This isn't just about moving to the AWS cloud. This is how real-world systems break, evolve, and get rebuilt into what comes next. If you think a senior AWS Cloud Migration interview is about reciting textbook service definitions, you have already failed. The industry pays for architects who can survive a 2 a.m. database split brain, a mid-flight ransomware attack, and a panicking CFO.
Here are 92 brutal, field-tested AWS production scenarios that will separate the AWS-certified beginners from the top 1% of AWS cloud architects.
This video series is structured like a real migration journey, not theory, not certification prep, but the exact scenarios architects face under pressure. Each chapter represents a phase of transformation, and each scenario is a decision point where things either scale or collapse based on how you respond.
Here are how that 92 brutal, field-tested AWS production scenarios are divided into 6 chapters of transformation.
We will navigate the migration through these 6 critical phases. Chapter 1, Strategy and Planning, where migrations succeed or fail before they even begin. Chapter 2, Data and Storage, moving petabytes without corruption, downtime, or loss. Chapter 3, Networking and Security, bridging on-prem and cloud without latency, exposure, or failure. Chapter 4, Execution and Cutover, the 2 a.m. war room rollback windows, split brain, and real outages. Chapter 5, Post-Migration Optimization, fixing cost explosions, latency issues, and security drift. Chapter 6, Modernization and 2026 plus Edge, GenAI, serverless refactoring, ARM, and multi-cloud evolution. Each chapter contains real production incidents and the architect-level logic needed to solve them. This is not about how AWS works. This is about how systems survive, scale, and evolve in the real world.
Let's start with Chapter 1, Assessment, Discovery, and Strategy.
This is the Mobilize phase where migrations are either won or lost. We are moving beyond architectural diagrams into the messy reality of undocumented dependencies, political resistance from engineering teams, and strict financial constraints. Success here requires a specialist who can audit an estate and determine exactly how to move without breaking the business.
Chapter 1, Scenario Overview.
Scenario 1 to 500 plus applications, limited budget and time. Scenario 2, migrating 1,500 undocumented virtual machines. Scenario 3, handling engineering resistance and skill gaps. Scenario 4, justifying refactoring versus lift and shift. Scenario 5, the anti-migration case for proprietary hardware. Scenario 6, adapting to a mid-flight 30% budget cut. Scenario 7, stabilizing a failing over budget migration. Scenario 8, the 30-day data center exit deadline. Scenario 9, handling zombie servers to improve TCO. Scenario 10, secure decommissioning and retire strategies. Scenario 11, licensing traps BYOL versus repurchase. Scenario 12, air-gapped HIPAA and GDPR validation. Scenario 13, divesting a subsidiary into a standalone account. Scenario 14, mitigating the migrate now, optimize later trap. Scenario 15 to 40, 5-day VMC on AWS versus native EC2 evacuation. Let's start with Scenario 1.
Scenario 1, you inherit 500-plus legacy apps, unknown dependencies, and a hard budget cap. Leadership wants visible progress in weeks, not months. What do you migrate first, and how do you avoid breaking the business?
Answer: I would approach this as a portfolio optimization problem rather than just a migration. 1. Run agentless discovery for breadth, then deploy agents only on top 20% critical systems to capture east-west traffic. Full agent rollout delays you by weeks with marginal signal gain. 2. Build a dependency graph from flow logs and process maps, then cluster apps using communication frequency. If you split a high chatter cluster across waves, expect cascading failures at cutover. 3. Score each app on a 2-axis matrix, business impact revenue or SLA versus migration complexity statefulness, data size, OS support. Pick low complexity, high impact first to prove ROI within the first wave. 4. Default to rehost for wave 1, but pre-tag candidates for replatform where OS is near end of life. Ignoring this creates a second migration later under worse conditions. 5. Define a hard downtime budget per app, for example, less than 15 minutes, and select replication method accordingly. If RPO and RTO isn't explicit, teams overpromise and you miss cutover windows. 6. Construct waves by dependency clusters, not org charts. Org-based waves look clean on paper, but fail when shared databases and auth services aren't migrated together. 7. Overlay cost telemetry early. Target underutilized VMs less than 20% CPU and high license stacks first. Missing this delays visible savings and weakens executive support. Pro tip: before Wave 1, execute a controlled failure drill. Simulate a cutover on a non-critical cluster and force a rollback. This surfaces hidden DNSTTL issues, connection retry bugs, and runbook gaps that won't appear in staging, but will break your first real weekend.
Scenario 2. You are tasked with migrating 1,500 undocumented virtual machines with no ownership clarity, unknown dependencies, and limited time. How do you discover, map, and group these systems into safe migration waves without breaking production?
Answer: treat this as a signal extraction and blast radius control problem. Reconstruct system intelligence before attempting any migration. 1. Start with agentless discovery to inventory all 1,500 VMs. Then deploy agents only on top 10 to 15% high traffic or high connection nodes identified via flow logs. Full agent rollout at this scale wastes weeks with minimal incremental visibility. 2. Establish baseline signals using CPU, memory, disk IOPS, and network flow logs over a 10 to 14-day window. Any VM with less than 5% utilization and no inbound connections is a strong candidate for retire or last wave migration. 3. Build a dependency graph from network flows and cluster VMs based on communication frequency and latency sensitivity. Splitting a high chatter cluster across waves will trigger cascading failures during cutover. 4. Identify hidden dependencies by correlating cron jobs, shared databases, file systems, and authentication services. Undocumented schedulers and shared storage are the most common causes of post-migration outages. 5. Form migration waves using dependency-aligned clusters and cap each wave to a controlled blast radius, for example, 50 to 100 VMs. Oversized waves make rollback coordination exponentially harder. 6. Prioritize stateless, batch, or low SLA workloads in initial waves to validate tooling, replication behavior, and rollback under real conditions before touching stateful or customer-facing systems. 7. Introduce a validation gate before each wave. Simulate failure scenarios such as partial replication, DNS lag, and network drops to ensure rollback works under stress, not just in clean test environments. Pro tip: ignore CMDB and ownership tags in undocumented environments. Derive ownership by analyzing login patterns and traffic sources. The team that generates and consumes the most traffic from a VM is its real owner, not what outdated documentation says.
Scenario 3. The CTO demands rapid cloud migration, but the engineering team resists due to skill gaps and risk concerns. Delivery is stalled. How do you handle this?
Answer: you're 3 weeks into a mandated migration. Velocity has completely flatlined, and the CTO is threatening to bypass your engineers with external contractors. The team is not communicating, and if this continues, you risk missing the Q3 delivery window entirely. At this point, I don't push harder on deadlines or mandate AWS training modules. That only breeds resentment and fragile architectures. I pivot to a strangler pilot approach by selecting a single low-risk batch workload that can be migrated within 3 to 5 days and deliberately pull in the most skeptical engineer to co-own the execution. Together, we implement strict IAM boundaries and automated rollback runbooks to prove that failure is controlled and reversible. This shifts the conversation from opinion to evidence. The key insight here is that engineering pushback is rarely stubbornness. It's a rational response to unquantified risk, and you don't overcome it with executive pressure. You overcome it by engineering psychological safety into the system. Pro tip: record this entire pilot migration as a step-by-step internal video playbook, including the mistakes and rollback steps. This eliminates repeated decision-making for future waves and quietly upskills the entire engineering team without the friction of formal training.
Scenario 4. The client insists on a lift and shift rehost for a large monolith. but you believe refactoring is necessary. How do you evaluate and justify the right approach?
Answer: frame this as a rehost versus refactor trade-off under time, risk, and business constraints optimized for current pressure without creating future failure. 1. Acknowledge the hard constraint. If the data center lease expires in less than 60 days, default to rehost. Attempting a refactor mid-flight guarantees broken services and a missed physical exit deadline. 2. Evaluate the network penalty. Rehosting preserves behavior, but moving a chatty monolith across availability zones introduces latency amplification and timeout failures under load. 3. Expose the cloud shock consequence. A pure rehost often requires over-provisioned EC2 to match on-prem peak capacity, typically increasing cloud costs by 30 to 50% until workloads are optimized. 4. Audit operational readiness. If the team lacks Kubernetes or serverless observability skills, a forced refactor will drastically increase MTTR during the first production incident. 5. Present the refactor advantage clearly. If the application has high growth, unpredictable traffic, or scaling bottlenecks. Refactoring enables elasticity, cost efficiency, and long-term resilience that rehosting cannot provide. 6. Check the application lifecycle. If the system is stable and feature frozen, rehost and contain it. Refactoring a stagnant application burns engineering effort with no measurable ROI. 7. Establish a strangler fig compromise. Rehost behind an application load balancer. Then incrementally extract high-traffic components into microservices to modernize without a big bang risk. 8. Call out the future failure trap. A rushed rehost without a funded Phase 2 plan will permanently lock technical debt into the cloud, making future modernization exponentially harder and more expensive. Pro tip: never refactor during the first migration wave of a critical system. Migrate it as is. Stabilize in the cloud, then capture real performance and usage data before deciding what to refactor. Otherwise, you risk redesigning based on assumptions, not reality.
Scenario 5. You are evaluating a legacy system dependent on specialized, proprietary hardware. Leadership mandates a 100% cloud migration, but you know this workload cannot move. How do you handle this?
Answer: you are finalizing the Wave 3 architecture board. When the CIO drops a hard mandate, everything goes to AWS, including a legacy hardware appliance processing real-time factory floor telemetry. There is no cloud-native equivalent, and attempting to emulate it on EC2 would introduce latency beyond its sub-millisecond tolerance, causing message queue backlogs and halting the physical assembly line. At this point, I don't argue cloud ideology, I argue physics. I map out the hard constraints: proprietary kernel drivers, strict vendor licensing that prohibits virtualization, and deterministic I/O requirements that cloud infrastructure cannot guarantee. Instead of a flat refusal, I pivot to a hybrid containment strategy. I keep the specialized hardware on premises, establish low-latency connectivity using Direct Connect and Transit Gateway, and expose the system through an internal network load balancer with controlled API interfaces for cloud services. This decouples the legacy system while allowing the rest of the platform to modernize safely. The key insight is that forcing every workload into the cloud isn't strategy, it's ideology. Real architecture decisions respect physical constraints over executive trends. Pro tip: if leadership insists on cloud-first compliance, propose AWS Outposts for this workload. It brings AWS infrastructure on-prem, satisfying governance requirements, while preserving the ultra-low latency and hardware dependencies that the system cannot function without.
Scenario 6. Midway through a migration planning phase, the client's business requirements change significantly, and their budget is slashed by 30%. How do you adapt your migration waves?
Answer: a 30% budget cut means the original architecture is dead. Do not try to optimize your way out of it. Ruthlessly alter scope, sequencing, and cost structure before capital runs out. 1. Halt modernization tracks. Any application requiring multi-week engineering effort must be forced into rehost using AWS Application Migration Service. Attempting partial refactors under budget pressure leads to fragmented architectures and stalled migration waves. 2. Abandon one-to-one hardware mapping. Use AWS Compute Optimizer with P90 CPU metrics to aggressively right-size EC2 targets, Sizing for peak on-prem workloads inflates month 1 cloud spend and accelerates budget exhaustion. 3. Rebuild migration waves based on ROI. Collapse waves to prioritize only revenue-generating and compliance-critical systems, migrating low-value workloads under reduced budget guarantees incomplete program delivery. 4. Enforce the retain penalty. Freeze the bottom 20% of low-traffic or internal apps on-prem. Every unnecessary migration consumes capital that should fund business-critical systems. 5. Quarantine high-cost dependencies. Identify Oracle/SQL Server workloads and pause migration, unless a clear BYOL or license manager strategy exists. Double licensing during transition can consume the remaining budget in a single wave. 6. Lock in baseline compute discounts. Commit to 1-year compute savings plans for confirmed workloads. Staying on-demand pricing under budget pressure guarantees financial overrun before migration completion. 7. Introduce a hard funding gate. Do not approve Wave 2 until Wave 1 actual AWS billing aligns with revised forecasts. Treating the reduced budget as a single pool leads to uncontrolled burn and mid-project collapse. 8. Call out the failure scenario explicitly. If scope, sizing, and licensing are not aggressively reduced within the first 2 waves, the migration will stall halfway, leaving systems split between on-prem and cloud with no budget to complete or roll back. Pro tip: when a CFO slashes a budget, they are usually flying blind. Implement AWS cost categories to map AWS tags directly to business units. When you prove that a non-critical migration is consuming a disproportionate share of the remaining budget, leadership will quickly approve scope reduction.
Scenario 7. A migration project is months behind schedule and wildly over budget. Stakeholders are panicking and threatening to cancel the program. How do you regain control and trust?
Answer: at this point, presenting a revised Gantt chart or asking for more runway is career suicide. The program is about to be canceled, and if it continues drifting, you risk a split brain estate with systems half in cloud and half on-prem with no budget to finish. The failure here isn't technical. It's a collapse of momentum caused by scope creep and analysis paralysis. I immediately freeze new scope intake and halt all in-flight modernization tracks, then pivot a strike team to a strict rehost-only path using AWS Application Migration Service. We select a single, highly visible, low-risk workload and force a production cutover within 10 to 14 days to prove safe execution in the VPC. I deliberately descope CI and CD perfectionism and non-critical hardening to compress time to value while enforcing a rollback-ready runbook. The key insight is that in a failing migration, stakeholders don't buy plans, they buy evidence. You restore trust with a working system in production, not with better documentation. Pro tip on day 1. Stop the financial bleed by hunting ghost infrastructure. Use AWS Cost Explorer and idle resource reports to find pre-provisioned RDS/EC2 environments waiting on delayed cutovers, and pause them immediately. This gives you instant burn rate reduction and political capital with the CFO.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, You can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The Elite Transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the Masterclass.
Scenario 8. You have a strict 30-day data center exit deadline, but the architectural documentation is completely missing or outdated. How do you safely migrate without breaking critical dependencies?
Answer: if you miss the lease expiration, the facility owner literally unplugs your racks, but waiting for a full discovery phase guarantees you run out of time. Blindly moving servers will sever hard-coded IPs, orphan shared databases, and trigger cascading outages across undocumented systems. In this scenario, I abandon all modernization and right-sizing. The goal is a digital evacuation with minimum change. I run rapid, signal-first discovery using AWS Application Discovery Service, agentless for breadth, and VPC flow log-style traffic capture to identify active TCP relationships over a tight 48 to 72-hour window, ignoring stale CMDB data. I cluster servers into dependency lifeboats based on communication frequency and replicate them with AWS Application Migration Service, MGN, using block-level replication. I overprovision target EC2 to match on-prem specs and preserve performance, and I freeze DNS/identity changes to avoid mid-flight resolution failures. The key insight is that, in an evacuation, cost and technical debt are acceptable collateral you can right-size later, but you cannot recover a decommissioned data center. Pro tip: do not re-IP during evacuation. Recreate equivalent CIDR ranges in your VPC and use AWS Transit Gateway with private routing to preserve address continuity. Lift the network as is, then refactor IP dependencies after stabilization.
Scenario 9. During discovery, you identify that 30% of the on-premises servers are zombies underutilized or inactive. How do you incorporate this into the migration case and wave plan?
Answer: treat zombie identification as an immediate ROI multiplier. Use empirical signals to eliminate waste before it enters your cloud cost structure. 1. Define strict zombie criteria. Servers with P95 CPU less than 3%, minimal inbound/outbound traffic, and no scheduled job execution over a 14-day window are candidates. Relying only on outbound traffic risks missing inbound only or event-triggered systems. 2. Execute a scream test on premises. Temporarily isolate suspected zombies at the network level for 48 to 72 hours. This reveals hidden dependencies like monthly batch jobs or audit processes that standard monitoring windows miss. 3. Validate dependency edges before retirement. Cross-check zombie candidates against database connections, authentication services, and shared file systems. Removing a silent dependency can break multiple active applications post-migration. 4. Pivot to a storage-only strategy. Instead of rehosting, archive dormant server data to S3 Glacier or low-cost storage tiers. Ensure data format and retrieval SLAs meet compliance requirements before decommissioning compute. 5. Recalculate the business case immediately. Remove zombie workloads from the target architecture and present updated TCO showing reduced EC2 footprint. Failing to do this early leads to inflated cloud budgeting and weak cost credibility. 6. Quarantine shadow zombies. Servers with high CPU but no network activity often indicate runaway processes or abandoned dev workloads. Migrating these directly results in unnecessary compute consumption and unpredictable cloud costs. 7. Enforce a retire-first policy. Require application owners to explicitly justify why a low-utilization server should be migrated. Defaulting to migration instead of validation guarantees cost inefficiency at scale. 8. Call out the failure trap. Migrating zombie workloads into AWS without validation creates permanent cost leakage. These instances rarely get revisited, and silently inflate monthly bills long after migration completes. Pro tip: use AWS Migration Evaluator to compare provisioned versus actual utilization, showing leadership that infrastructure is over-provisioned by 3 to 4 times on-prem is the fastest way to justify retiring a large portion of the fleet and securing early cost wins.
Scenario 10. You need to securely decommission legacy applications during the migration without breaking unknown downstream dependencies. How do you execute a retire strategy safely?
Answer: treat decommissioning as a controlled scream test. Gradually sever dependencies while maintaining a rapid rollback path to prevent permanent disruption. 1. Implement inbound traffic silencing. Use security groups or host-level firewall rules to block ingress traffic while keeping the server running for 3 to 7 days. This exposes hidden dependencies through timeouts while preserving full system state for instant rollback. 2. Preserve rollback artifacts. Capture AMIs or VM snapshots and retain DNS records before shutdown. Without a rollback path, a failed retire attempt turns into a full recovery incident. 3. Audit DNS and connection patterns. Analyze DNS query logs and active connections to detect hard-coded IPs or legacy integrations. Missing even one undocumented dependency can break downstream services post-retirement. 4. Decouple and archive data safely. Export database snapshots and logs to S3, then transition to Glacier tiers for long-term retention. Never move live databases directly to archive storage without preserving structure and recovery options. 5. Validate dependency edges. Cross-check connections to shared services like authentication, reporting, and batch schedulers. Many retired apps still act as silent providers for other systems. 6. Enforce a time-boxed retire decision. Limit investigation to a 7 to 10-day window per application cluster. Over-analysis often costs more than rehosting the system temporarily. 7. Execute DNS cleanup with intent. Remove stale DNS records and redirect traffic to a controlled 410 gone endpoint. This provides immediate visibility into forgotten clients still calling the retired service. 8. Call out the failure trap. Retiring systems without validating dependencies creates hidden outages that only surface weeks later, making root cause analysis significantly harder. Pro tip: never trust an application owner who claims there are no dependencies. Run a QuickNet stat or connection trace on the server to identify active external connections. This often reveals undocumented integrations that would otherwise break silently after decommissioning.
Scenario 11. A critical application has strict, expensive on-premises licensing Oracle/SQL Server. How do you decide between rehost BYOL versus repurchase SaaS or PaaS?
Answer: treat licensing as the primary cost driver. Map entitlements to cloud architecture before choosing migration strategy to avoid compliance risk and cost explosion. 1. Validate license mobility and hosting terms. If software assurance or equivalent mobility rights are missing, BYOL may require dedicated hosts or other restrictions. Misinterpreting vendor terms can trigger compliance violations and unexpected infrastructure costs. 2. Model the scaling constraint of BYOL. Running on dedicated or license-bound infrastructure limits auto-scaling and spot usage, forcing vertical scaling. This preserves license investment but sacrifices cloud elasticity and cost efficiency. 3. Quantify the repurchase break-even point. RDS license included increases hourly cost but removes annual maintenance fees. If utilization is less than 60 to 70%, for example, dev/test or burst workloads, LI often becomes cheaper than BYOL over time. 4. Enforce license boundaries with AWS License Manager. Cap vCPU/core visibility to match entitlements. Without this, elastic scaling can exceed license cores and trigger audit penalties larger than the migration cost itself. 5. Check edition and feature dependencies. Enterprise-only features, for example, partitioning. Advanced HA may force higher cost SKUs in cloud. Overlooking this leads to unexpected upgrades or application rewrites mid-migration. 6. Evaluate SaaS/PaaS lock and trade-offs. Repurchasing eliminates infrastructure overhead but may restrict direct database access. If existing BI/reporting tools depend on SQL-level access, You may need costly API-based integrations. 7. Optimize compute to match licenses. Use features like optimize CPUs to align instance vCPU count with license limits. Failing to do this results in paying for unused cores and effectively doubling licensing cost. 8. Pivot to an open source refactor. If BYOL audit risk and SaaS lock-in are both unacceptable, insert an interim phase to migrate SQL Server to Aurora Postgres SQL via Babelfish. Skipping this locks you into another 3-year commercial contract. Pro tip: for SQL Server, leverage the passive failover benefit with software assurance. You can run a secondary passive instance for HA without requiring a second license, cutting disaster recovery licensing costs nearly in half compared to traditional on-prem clusters.
Scenario 12. A healthcare client has strict air-gapped compliance, mapping HIPAA/GDPR. How do you validate that the target AWS environment meets these laws before any data moves?
Answer: at this stage, moving even a single test record is a liability you cannot retrofit compliance after ingestion. I first confirm the business associate addendum is executed and that every AWS service in scope is HIPAA eligible, because eligibility does not equal compliance. I then codify controls, deploy AWS config with HIPAA/GDPR conformance packs to continuously enforce encryption at REST S3, EBS, RDS and TLS 1.2 plus in transit, and block non-compliant resource creation in real time. Next, I establish a data perimeter using service control policies combined with VPC endpoints, and S3 block public access so data never traverses the public internet or leaves the approved region. I enforce customer-managed KMS keys with strict key policies, rotation, and least privilege access to ensure cryptographic control is auditable. Finally, I validate auditability with Cloud Trail, centralized logging, and guardrails that alert on any drift from policy. The key insight is that in healthcare, your MVP is minimum viable compliance if your guardrails cannot prevent a misconfigured bucket or unencrypted volume at creation time. The environment is not ready for a single byte of PHI. Pro tip: use AWS Artifact to download SOC 2 and ISO 27001 reports for each in-scope service, and attach them to your authority to operate package. Pair this with an AWS Audit Manager evidence report to give legal and compliance teams pre-built, auditable proof. This short-circuits months of review cycles.
Scenario 13. A company is divesting a subsidiary and must fully separate its workloads from the parent's data center within a strict Transition Service Agreement (TSA) deadline. Shared networks, identity systems, and databases exist. How do you execute a clean and legally compliant separation?
Answer: this is not a migration, it is a legal and operational severance. Any leftover dependency after the TSA deadline becomes a compliance violation or financial liability. 1. Establish a legally isolated AWS organization using Control Tower within the first 48 to 72 hours. Delaying account separation risks data commingling and audit violations under financial and regulatory review. 2. Create a clean room landing zone and migrate workloads directly into it. Staging inside the parent environment creates hidden dependencies that survive past TSA and block full separation. 3. Implement temporary connectivity using Transit Gateway with strict allow lists and expiry rules. If not removed before TSA, this becomes an undocumented backdoor between parent and subsidiary networks. 4. Execute direct block-level replication into new accounts using AWS MGN. Double hop migrations through shared environments increase cutover risk and extend timelines beyond TSA limits. 5. Rebuild DNS and service discovery from scratch using Route 53. Retaining parent DNS references causes immediate service resolution failures after final network cutover. 6. Decouple identity using a new IAM identity center or directory service. Continued reliance on parent Active Directory creates a post-separation security vulnerability and operational dependency. 7. Transfer data ownership using account-level resource reassignment and KMS key re-encryption. If encryption keys remain under parent control, the subsidiary does not legally own its data. 8. Implement independent billing and cost allocation from day one, using AWS organizations and cost categories. Shared billing creates legal and tax disputes after financial separation. 9. Run a pre-TSA severance audit using AWS Config and IAM Access Analyzer to detect cross-account trust. Even a single leftover role allows unauthorized access after legal separation. 10. Call out the failure scenario explicitly. If identity, DNS, or network dependencies remain at TSA expiry, the subsidiary becomes operationally dependent with no support contract, leading to outages, legal escalation, and emergency re-architecture. Pro tip: the hardest dependency to break is operational. Stand up a separate service catalog and support workflow in week 1. If engineers still rely on the parent's IT system, the separation has already failed regardless of technical architecture.
Scenario 14. A high-growth retail client demands a lift and shift-only strategy to exit their data center before a holiday peak, explicitly banning any refactoring. They plan to optimize later, but your analysis shows the legacy monolith will bleed costs and fail under elastic demand. How do you mitigate this strategic trap?
Answer: blindly following this mandate guarantees a double failure. Day 1 cloud bills will spike due to over-provisioned instances, and the application will still crash under burst traffic because a raw rehost does nothing to fix legacy I/O and scaling bottlenecks. I don't fight the timeline. I redefine the safe rehost by introducing a pre-cutover right-sizing gate using AWS Compute Optimizer to eliminate excess capacity before replication even starts. To protect the monolith from holiday spikes, I front it with an application load balancer and configure auto-scaling with conservative thresholds to absorb traffic at the edge. Instead of a full database refactor, I implement targeted storage tuning, moving to GP3 volumes with provisioned IOPS and offloading read-heavy traffic to an RDS read replica to reduce lock contention. The key insight is that optimize later is a myth. If you don't control cost and load behavior during the move, the cloud will simply amplify your existing inefficiencies at a higher price point. Pro tip: tag every resource in this fast-track wave with an optimization debt key and attach a 60 to 90-day budget impact estimate. When you convert technical debt into a monthly dollar amount, leadership stops treating optimization as a luxury and starts funding it as a financial priority.
Scenario 15. A financial services firm lost their data center lease and has exactly 45 days to evacuate 200 VMware-based critical applications. They must choose between the speed of VMC on AWS and the lower cost of native EC2. What is your move?
Answer: this is a time-constrained evacuation, not a cost optimization exercise. Prioritize migration velocity and operational continuity, then optimize after the exit. 1. Select VMware Cloud VMC on AWS as the primary landing zone to preserve existing VMware constructs. Choosing native EC2 introduces server conversion overhead that adds 1 to 2 hours per VM, making a 45-day deadline mathematically impossible. 2. Acknowledge the 20 to 30% infrastructure cost premium of VMC as an insurance policy. This expense is negligible compared to the legal penalties and business disruption costs of a failed data center exit. 3. Establish high-throughput connectivity using AWS Direct Connect with VMware HCX. Attempting to migrate 200 VMs over standard VPN will bottleneck bandwidth and extend replication timelines well beyond the available window. 4. Adopt a migrate to convert strategy. Evacuate the workloads to VMC first to secure the facility exit, then schedule a phased conversion to native EC2 or containers only after the physical lease has legally terminated. 5. Enforce a strict throughput target of 5 to 7 VM cutovers per day. Falling below this rate within the first 10 days is a leading indicator of systemic network bottlenecks that will cause a project-wide failure. 6. Apply a temporary 1-to-1 hardware sizing rule during the evacuation. Attempting to right-size 200 workloads during the move adds significant analysis overhead that delays the bulk movement of critical data. 7. Monitor for stranded workloads. Any VM failing its heartbeat check during the initial HCX sync must be prioritized for an offline snowball edge transfer immediately to prevent it from missing the final shutdown window. Pro tip: use HCX bulk migration to execute cutovers in controlled batches of 15 to 25 VMs per night. This allows you to validate network routing and application health on a small group, while the remaining workloads continue replicating, preventing a last-day mass outage.
Chapter 1 Conclusion.
We have officially secured the strategic foundation of the Mobilize phase. From legacy discovery to budget triage, you now have the senior-level framework required to lead a complex migration program. Strategy is now set. The next challenge is technical execution.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Chapter 1 to Chapter 2 Transition to Technical Execution.
Moving from planning to execution means confronting data gravity. Petabytes of unstructured data and mission-critical databases do not move easily. We now shift our focus from architectural frameworks to the raw mechanics of data replication and schema conversion.
Chapter 2 Data, Storage and Database Migrations.
This chapter covers the deep technical hurdles of moving stateful workloads. We will solve for zero-downtime cutovers, storage performance parity, and handling mid-flight data corruption. This is where a cloud migration specialist proves their value in the logs.
Chapter 2 Scenario Overview.
Scenario 16, migrating 2 petabytes of unstructured data with poor bandwidth. Scenario 17, 10 terabytes Oracle database with less than 5 minutes downtime. Scenario 18, remediating 30% SCT schema incompatibility. Scenario 19, migrating petabyte-scale physical tape archives. Scenario 20, high IOPS block storage migration to Amazon EBS. Scenario 21, handling mid-flight data corruption on NAS appliances. Scenario 22, continuous data replication to Amazon Redshift. Scenario 23, troubleshooting post-migration data inconsistency. Scenario 24, migrating real-time analytics with high ingestion. Scenario 25, relieving source pressure during 50 terabytes DMS tasks. Scenario 26, migrating millions of hard-coded IoT MQTT devices. Scenario 27, tuning data sync for millions of fragmented files. Scenario 28, secure PII chain of custody via AWS Snow family. Scenario 29, managing staggered app/DB migration latency. Scenario 30, masking failovers with Amazon RDS proxy. Next, we break down the technical execution for each of these high-stakes scenarios.
Scenario 16. A company has 2 petabytes of unstructured data stored across multiple data centers with incredibly poor network bandwidth. How do you migrate this data to Amazon S3?
Answer: at 2 petabytes, network transfer is a physics impossibility. You must pivot to physical data transport to avoid a multi-year migration timeline. 1. Deploy AWS Snowmobile for a single site 2 petabytes ingestion, while multiple Snowball edge units allow for parallel loading. The logistical overhead of managing 25 plus separate devices and local network hookups creates a massive margin for human error and data fragmentation. 2. Enforce a 256-bit end-to-end encryption requirement using AWS KMS before the truck leaves the data center. Failing to secure the hardware during transit creates a catastrophic compliance breach if the physical vehicle is compromised or intercepted. 3. Implement a pre-migration checksum validation MD5/SHA-256 on the source files. Without a baseline hash, you cannot programmatically prove data integrity after the Snowmobile ingest, leading to silent data corruption in your new S3 data lake. 4. Provision a high-speed 40 Gbps local network bridge directly to the Snowmobile. Using existing 1 Gbps infrastructure will bottleneck the hardware's ingest capability, extending the on-site transfer window from weeks to months and risking timeline failure. 5. Architect an S3 lifecycle policy immediately upon ingest to move data to S3 intelligent tiering. Without automated tiering, 2 petabytes of hot storage can generate a 6-figure monthly cost greater than $100,000 for data that is rarely accessed. 6. Sync the data delta using AWS Data Sync over the wire after the bulk Snowmobile load is complete. Since a 2 petabytes physical move takes weeks to ship and ingest, failing to capture incremental changes will result in stale datasets and require a second migration cycle. 7. Enforce S3 object lock for regulated datasets during bucket creation. If immutability is not configured upfront, you cannot meet worm compliance requirements without a full recopy of petabyte scale data. 8. Call out the failure mode explicitly. Attempting a network-only migration for 2 petabytes across low bandwidth links less than 1 Gbps will extend the timeline into years, causing program delays and potential cancellation by leadership. Pro tip: perform a small batch test of 1 terabytes locally before the Snowmobile arrival. This reveals local disk read bottlenecks and network MTU mismatches that would otherwise stall a 2 petabytes transfer early, saving weeks of troubleshooting.
Scenario 17. A financial system runs a heavily transactional 10 terabytes Oracle database and requires less than 5 minutes of downtime during the cutover. Outline your strategy using AWS DMS and CDC.
Answer: this is a precision cutover where schema conversion and continuous replication must be perfectly synchronized to minimize the final delta sync window. 1. Run the AWS Schema Conversion Tool (SCT) to identify PL/SQL objects that cannot be automatically mapped. Failing to manually remediate these red objects before starting DMS will result in broken application logic post-cutover. 2. Deploy AWS DMS with full load plus CDC change data capture and enable supplemental logging on the source Oracle DB. Without supplemental logging, DMS cannot capture the data changes during the multi-day full load, leading to immediate data divergence. 3. Set target table prep mode to do _nothing after the initial schema load. If you leave it at drop _ create, DMS will wipe your SCT optimized indexes and constraints, causing the target database to crawl under production load. 4. Isolate LOB large object columns into a separate DMS task. LOBs are memory intensive and slow, and failing to separate them will bottleneck replication and push CDC lag beyond acceptable limits less than 30 seconds. 5. Provision the DMS replication instance with sufficient memory, for example, R5/R6 class with greater than 64 GB RAM to handle transaction buffering. Under provisioning will cause task crashes during peak write bursts. 6. Establish a final cutover buffer. Stop application writes, wait for CDC latency to reach 0, and complete the switch within the less than 5-minute downtime window. Skipping the latency check guarantees loss of recent transactions. 7. Implement AWS DMS validation to verify row counts and checksums between Oracle and Aurora. Without validation, data inconsistencies may go undetected and surface weeks later in production. 8. Call out the failure mode explicitly. If CDC latency is not controlled and validated before cutover, the migration will appear successful but silently lose transactions, leading to financial inconsistencies and business-critical reconciliation failures. Pro tip: for 10 terabytes Oracle migrations, use DMS parallel load to split large tables into segments. This reduces full load duration and keeps CDC lag manageable, increasing the probability of meeting the less than 5-minute cutover window.
Scenario 18. You are migrating an outdated on-premises SQL server, but the AWS Schema Conversion Tool, SCT, reports that 30% of the objects cannot be automatically converted to Amazon Aurora. What is your remediation strategy?
Answer: the SCT report confirms that 30% of your stored procedures and triggers are red, and a full manual rewrite will extend the migration timeline by approximately 2 to 3 months, blocking the data center exit. At this point, I do not force a broken conversion. I isolate whether the incompatibility is due to proprietary TSQL features or complex business logic. I immediately pivot the strategy for those specific workloads to Babelfish for Aurora Postgres SQL, which allows the database to understand TSQL commands without a full code rewrite, but only after validating feature compatibility to avoid runtime failures. If Babelfish lacks support for critical features, I shift to a tactical replatform to Amazon RDS for SQL Server to preserve application behavior within the fixed timeline constraint. The key insight is that the refactor objective is secondary to the exit objective. Forcing a rewrite under time pressure introduces both functional defects and schedule risk. If this decision is mishandled, the migration will either miss the deadline or deploy a partially functional system that fails under production workloads. Pro tip: check for linked server dependencies and execution frequency. In many legacy environments, 20 to 30% of flagged incompatible objects are rarely used or dormant, and removing them from scope can immediately reduce the effective incompatibility without writing new code.
Scenario 19. A company has petabyte-scale cold data archives on tape drives. How do you migrate this to Amazon S3 Glacier cost-effectively while ensuring long-term accessibility?
Answer: tape migration is a logistics and retrieval cost challenge. You must balance the time to data versus the cost of storage using a virtualized ingest approach. 1. Deploy AWS Storage Gateway in tape gateway mode to emulate physical tape libraries. This allows your existing backup software to write directly to virtual tapes in S3 without changing workflows, and failing to do so forces application-level rewrites that delay the migration program. 2. Select S3 Glacier Deep Archive for datasets with greater than 180-day retention requirements. Using S3 Standard for petabyte-scale cold archives can increase storage costs by 20 to 25 times without delivering any access benefit. 3. Utilize offline transfer via AWS Snowball Edge if the available bandwidth is less than 1 Gbps. Attempting to transfer petabytes over limited network links will throttle production systems and extend the migration timeline into months or years. 4. Enable S3 Object Lock for compliance-sensitive archives at bucket creation. Failing to enforce immutability upfront creates regulatory violations and requires a full recopy of petabyte-scale data to correct. 5. Define retrieval patterns before final tier selection. For example, less than 1% monthly access. Ignoring access behavior can result in unexpected 6-figure retrieval costs when large datasets are restored. 6. Automate tape lifecycle management using AWS Backup. Relying on manual processes leads to inconsistent retention enforcement and leaves data stranded in higher-cost storage tiers. 7. Perform periodic random restore validation. For example, 1 to 5 terabytes test restores. Without validation, corrupted or unreadable archives will only be discovered during critical recovery scenarios. 8. Call out the failure mode explicitly. Treating tape migration as simple storage offload without retrieval planning results in either unusable archives during legal/audit requests or uncontrolled cost spikes, causing business and compliance failure. Pro tip: use Snowball Edge integrated with Tape Gateway for initial ingestion. This preserves existing backup workflows while bypassing network limits, enabling a seamless transition from physical tapes to virtual tape libraries.
Scenario 20. You are migrating a highly stateful legacy application attached to massive, high I/O storage arrays. How do you handle the block storage migration to Amazon EBS without performance degradation?
Answer: performance parity on AWS requires matching not just size, but latency and throughput. You must architect for the EBS throughput ceiling. 1. Select Amazon EBS IO2 block express volumes for workloads requiring greater than 16,000 IOPS and sub-millisecond latency. Using GP3 for high-performance databases will lead to I/O wait spikes and application timeouts during peak load. 2. Enable EBS-optimized EC2 instances with sufficient bandwidth, for example, greater than 10 Gbps EBS throughput. Deploying high IOPS volumes on underpowered instances will bottleneck storage performance regardless of volume configuration. 3. Transition to GP3 volumes for standard workloads and explicitly provision IOPS and throughput, for example, 3,000 to 16,000 IOPS. Failing to decouple performance from size leads to over-provisioning and unnecessary cost increase. 4. Implement RAID 0 striping across multiple EBS volumes when throughput requirements exceed single volume limits. Using a single volume creates a hard throughput ceiling that cannot support high-performance workloads. 5. Monitor cloud watch metrics such as volume queue length greater than 1 per 1,000 IOPS and burst balance continuously after cutover. Ignoring these signals results in hidden storage bottlenecks that degrade application performance under load. 6. Pre-warm EBS volumes created from snapshots by reading data blocks, for example, full scan of 1 to 5 terabytes datasets. Failing to pre-warm introduces high first read latency that slows the application immediately after migration. 7. Use multi-attach EBS volumes only for cluster-aware applications designed for shared block storage. Applying it to non-clustered systems leads to write conflicts and potential data corruption. 8. Call out the failure mode explicitly. If storage performance is not matched to baseline IOPS and latency requirements, the application will experience transaction delays, timeouts, and forced rollback under live traffic, causing business-critical outages. Pro tip: capture real workload characteristics using tools like FIO before migration. Matching AWS storage configuration to observed P99 latency and peak IOPS avoids both under-provisioning failures and expensive over-provisioning.
Scenario 21. A client wants to migrate terabytes of unstructured data from NAS appliances to Amazon FSx, but their on-premises deduplication software has corrupted a small percentage of files. How do you handle the corrupted data mid-flight?
Answer: I treat this as a migration continuity problem, not a data repair exercise. If I attempt to fix the deduplication corruption mid-flight, the entire migration stalls and risks missing the cutover window. I immediately configure AWS Data Sync to bypass strict end-to-end verification, so that corrupted blocks do not fail the entire transfer, isolating approximately 2% of unreadable files instead of blocking 100% of the dataset. I pivot to an S3-based quarantine zone, where a manifest-level hash comparison identifies and segregates corrupted objects into a controlled dead letter prefix for remediation. The healthy 98% of data is allowed to continue into Amazon FSx without delay, while the corrupted subset is handed off for tape-based recovery or backup restoration. The key insight is that migration velocity must be decoupled from data remediation under time pressure. If this separation is not enforced, the migration will halt and fail to meet delivery timelines. Pro tip: after recovery is complete, use the data sync transfer only change data option to backfill only the repaired files. This avoids reprocessing multi-terabyte datasets and keeps the final sync window within acceptable limits.
Scenario 22. You are migrating an on-premises data warehouse to Amazon Redshift, but the client requires continuous data replication from active transactional databases during the multi-week sync. How do you set this up?
Answer: to prevent data staleness during a 2 to 4 week migration window, you must architect a parallel path ingest strategy that separates bulk history from live transactional deltas. 1. Deploy AWS SCT data extraction agents for bulk historical loads across multiple nodes, for example, greater than 10 terabytes per day throughput. Relying on a single-threaded migration path will stall ingestion and extend the migration beyond acceptable timelines. 2. Configure AWS DMS with change data capture CDC targeting Amazon S3 as an intermediary layer. Writing CDC directly into Redshift causes excessive commit overhead and degrades cluster performance under high-frequency updates. 3. Use Redshift autocopy to batch ingest CDC files from S3 into staging tables. Without batching, continuous small inserts will fragment tables and trigger frequent vacuum operations, reducing query performance. 4. Implement a view-based merge strategy union all between historical and CDC tables. Directly merging into large fact tables during migration will create locking contention and significantly slow down both ingestion and query workloads. 5. Select Redshift Array3 instances with managed storage sized for growth, for example, scaling from 10 terabytes to 50 terabytes during migration. Under provisioning storage will cause ingestion failures and cluster instability. 6. Enforce workload management WLM queues to prioritize ingestion over analytics queries. Without query isolation, heavy reporting workloads will increase CDC lag and cause stale data in downstream analytics. 7. Validate data integrity using SCT validation on sampled partitions, for example, 5 to 10% of datasets. Skipping validation allows aggregation mismatches to propagate into production dashboards unnoticed. 8. Call out the failure mode explicitly if CDC ingestion and bulk load are not decoupled and controlled. Replication lag will grow uncontrollably, resulting in stale analytics data and eventual migration failure at the program level. Pro tip: offload cold historical data, for example, greater than 3 years old to S3 and query it using Redshift Spectrum. This reduces cluster size, accelerates migration, and significantly lowers storage and compute costs.
Scenario 23. After a partial data migration, the client reports severe data inconsistency issues between the cloud and on-premises environments. How do you troubleshoot and fix the sync?
Answer: I treat this as a control plane failure rather than a simple sync issue. If write traffic continues during investigation, divergence will increase and make reconciliation exponentially harder. I immediately freeze writes across both environments and use AWS DMS validation to identify drift at the row level, focusing on metrics like CDC latency, for example. Greater than 60 seconds indicates replication lag beyond acceptable limits. I then isolate the root cause, whether it is missing supplemental logging, a failed checkpoint, or network interruption, and re-establish CDC from a known consistent position, such as a system change number SCN. Only the affected tables are resynchronized using a targeted reload instead of rerunning the entire dataset. The key insight is that without enforcing a single source of truth during recovery, the system continues to propagate inconsistent data, and if left unresolved, the migration will fail at a program level due to data integrity loss. Pro tip: enable DMS validation before starting migration. It adds overhead, but it detects inconsistencies early and prevents large-scale resync operations later.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Scenario 24. You are tasked with migrating a real-time analytics workload with incredibly high ingestion rates. Which AWS services do you target, and how do you prevent data dropping?
Answer: high ingestion migrations, for example, 100,000 plus TPS or greater than 500 megabytes per second, require a pressure relief architecture that buffers spikes and guarantees durability before processing. 1. Implement Amazon MSK as the primary ingestion buffer with multi-broker replication, for example, replication factor equals 3. Without a durable commit log, downstream failures will result in permanent data loss during the migration window. 2. Configure Kinesis Data Firehose to stream a raw backup of all events to S3 without a secondary durable copy. Any pipeline failure requires data reconstruction, which is impossible for real-time streams. 3. Enable enhanced fan-out on Kinesis data streams for multiple consumers without dedicated throughput per consumer. Read contention will cause throttling and increase processing lag. 4. Enforce producer-side retries with exponential backoff and local buffering. If ingestion endpoints become temporarily unavailable, lack of retry logic leads to immediate and irreversible data loss. 5. Use provision throughput for Kinesis streams size to peak load, for example, 2 times baseline ingestion rate. Relying on on-demand scaling may not keep up with sudden spikes and can lead to dropped records. 6. Monitor cloud watch metrics such as incoming records versus outgoing records and maintain lag within acceptable thresholds, for example, less than 30 seconds. Ignoring backlog growth results in buffer overflow and data loss. 7. Use AWS Private Link for ingestion traffic to minimize network variability. Relying on public internet paths introduces latency spikes and producer timeouts under high throughput conditions. 8. Call out the failure mode explicitly. If ingestion buffering and retry mechanisms are not correctly implemented, high throughput spikes will overflow the pipeline, resulting in unrecoverable data loss and failure of the analytics system. Pro tip: enable MSK tiered storage when ingestion exceeds sustained disk capacity. This allows retention of multiple days of data at lower cost, giving you a recovery window to reprocess data if downstream systems fail.
Scenario 25. During an AWS DMS replication task for a 50 terabytes database, you notice the source database performance is severely degrading, impacting active users. How do you relieve pressure on the source?
Answer: I treat this as a source protection problem, not a migration acceleration problem. If the migration continues unchecked, source CPU saturation, for example, greater than 90% will impact production users and force an emergency shutdown. I immediately reduce DMS parallelism by lowering max full load subtasks, for example, from 8 to 2 to 3 to decrease concurrent read pressure on the source. I then analyze whether full table scans are being triggered due to missing primary keys and introduce parallel load segmentation on index columns to reduce scan intensity. I tune parameters such as commit rate and batch apply timeout to reduce log read frequency and contention on the source system. If pressure persists, I pivot the migration source to a read replica to isolate production workload from migration traffic. The key insight is that migration must remain invisible to users. If not controlled, the migration will degrade performance to the point where it must be halted, causing delays and program-level impact. Pro tip: switch from full LOB mode to limited LOB mode, for example, 32 kilobytes. Full LOB retrieval forces row-by-row fetches, which significantly increases load on the source database during large-scale migrations.
Scenario 26. A client with a massive IoT ecosystem wants to migrate their MQTT brokers to AWS IoT Core, but millions of edge devices have hard-coded endpoint URLs. How do you migrate without bricking the field devices?
Answer: I treat this as a network redirection problem rather than a device update problem. Attempting firmware updates across millions of devices introduces a 10 to 15% failure risk due to connectivity interruptions, which can permanently brick devices in the field. I implement DNS level redirection, using a CNAME to point the existing hard-coded domain to the AWS IoT Core data at its endpoint, ensuring devices continue operating without modification. For devices using hard-coded IPs, I deploy a proxy or NAT translation layer to redirect traffic transparently to the cloud endpoint. This allows all devices to continue functioning while migration happens behind the scenes. The key insight is that forcing change at the edge increases failure probability, and if not handled correctly, can result in large-scale device loss and migration failure. Pro tip: monitor DNS traffic patterns before final cutover. If certain regions still resolve legacy endpoints due to caching, keep the old broker running as a forwarder for 30 days to prevent device drop-offs.
Scenario 27. A media company is migrating millions of tiny, fragmented files using AWS Data Sync, but the transfer is throttling and taking 10 times longer than estimated. How do you tune the performance?
Answer: small file migrations are IOPS bound, not bandwidth bound. You must optimize metadata operations to avoid exponential slowdown. 1. Deploy multiple AWS Data Sync agents in parallel and distribute source paths across them, for example, 4 to 8 agents. Relying on a single agent creates a metadata processing bottleneck that results in 10 times slower transfers. 2. Disable copy ownership and copy permissions where POSIX fidelity is not required. Each metadata operation triggers additional API calls, and failing to disable them increases transfer overhead significantly for millions of files. 3. Tune task settings by setting verification mode to verify only transferred data and increasing task concurrency. Running full verification across millions of files will consume the entire migration window without meaningful data movement. 4. Monitor NAS IOPS limits, for example, greater than 10,000 metadata ops per sec, and throttle data sync accordingly. Exceeding source storage limits will degrade production performance and force an emergency stop of the migration. 5. Implement an archive before transfer strategy by bundling small files into larger chunks, for example, 500 megabytes to 1 gigabytes archives. Failing to reduce file count keeps the metadata overhead dominant and prevents throughput improvement. 6. Use VPC endpoints for S3 to keep traffic within the AWS backbone. Routing over the public internet introduces latency and packet loss that disrupts small file transfers. 7. Apply include/exclude filters to eliminate non-critical files, for example, temporary files, .ds_store. Scanning unnecessary files increases agent memory usage and delays actual data transfer. 8. Call out the failure mode explicitly if metadata operations are not optimized. Data sync agents will stall or crash under memory pressure, causing the migration to miss deadlines and fail at the program level. Pro tip: if targeting Amazon EFS, switch to Max I/O performance mode for high concurrency workloads. General purpose mode introduces latency per operation, which becomes a bottleneck for millions of small file transfers.
Scenario 28. You need to securely extract, transport, and ingest sensitive PII from a highly classified, air-gapped facility. How do you ensure end-to-end encryption and chain of custody?
Answer: in classified migrations, Cryptographic assurance and physical custody must be enforced together to prevent tampering and compliance violations. 1. Select AWS Snowball Edge with TPM-enabled hardware security. If the device is physically tampered with during transit, the TPM triggers key destruction, preventing unauthorized data access. 2. Enforce server-side encryption using AWS KMS with controlled key access. Allowing keys to exist outside AWS control introduces a risk of unauthorized decryption and compliance failure. 3. Generate and verify job manifest and signature files before and after transit. Without cryptographic validation, you cannot prove that data was not altered or replaced during shipment. 4. Perform full checksum validation, for example, SHA 256 on all data prior to transfer. Skipping integrity validation allows corrupted or altered PII to be ingested into the target system undetected. 5. Use Snowball devices with high-speed interfaces, for example, 10 Gbps SFP+, and ensure facility compatibility. Falling back to 1 Gbps transfer speeds extends loading time from days to weeks and risks missing secure transport windows. 6. Monitor device tracking and telemetry during transit using AWS console tools. Lack of visibility into device location and condition violates chain of custody requirements. 7. Enable S3 object lock in compliance mode for retained data, for example, 7-year retention. Without immutability enforcement, stored PII can be modified or deleted, breaking regulatory requirements. 8. Call out the failure mode explicitly. If encryption, validation, and custody controls are not enforced, the migration can result in undetected data tampering or loss, leading to severe compliance violations and program failure. Pro tip: use a non-sensitive decoy dataset on the Snowball to validate encryption and decryption workflows during audits. This allows verification without exposing actual classified PII.
Scenario 29. You are executing a staggered migration where the database moves to AWS today, but the application servers must remain on premises for another 6 months. How do you secure data in transit and handle latency?
Answer: I treat this as a latency amplification and security boundary problem, rather than a simple network extension. If left unaddressed, even a 10 milliseconds round-trip latency, with applications making 50-plus database calls per request, will increase response time from approximately 1 second to 5 to 6 seconds, severely degrading user experience. I establish AWS Direct Connect with a dedicated high-throughput link, for example, 10 Gbps, to reduce jitter and maintain consistent latency between on-prem and cloud. To mitigate latency impact, I introduce a read-aside caching layer using Amazon Elasticache or on-prem Redis to offload 70 to 80% of repeated queries. I enforce mutual TLS/MTLS for all database connections to secure data in transit across the hybrid link. The key insight is that when compute and data are split across environments, you must reduce round trips or bring compute closer. If not controlled, the application becomes unusable and the migration fails at a program level. Pro tip: tune TCP keepalive and connection pooling settings, for example, Hikari CP, to handle intermittent latency spikes. Without proper tuning, transient network delays will cause connection resets and application instability during the transition period.
Scenario 30. The application team refuses to modify their legacy code to handle the brief connection drop during a database DNS cutover. How do you use Amazon RDS proxy to mask the failover?
Answer: I treat this as a connection continuity problem rather than an application change issue. If the application loses its database connection for even 500 milliseconds, it crashes and requires manual intervention, which is unacceptable during cutover. I insert Amazon RDS proxy as the stable endpoint and route all application traffic through it, allowing the proxy to maintain persistent connections while switching the backend database during failover. I configure the proxy with AWS Secrets Manager for credential management, so the application does not directly interact with database authentication. I tune proxy connection pool settings to handle peak demand, for example, 2 times expected connection load to prevent exhaustion during failover events. The key insight is that RDS proxy acts as a buffer between fragile applications and infrastructure changes. Without it, connection drops during DNS cutover will cause application crashes and disrupt the migration, leading to program-level failure. Pro tip: monitor the database connections and client connections metrics on RDS proxy. If the pool is undersized, connection starvation will recreate the same failure scenario you are trying to avoid.
Chapter 2 Conclusion.
We have completed the most data-intensive phase of the migration lifecycle. By mastering the physics of moving petabytes of data and the precision required for zero-downtime database cutovers, you have secured the most vulnerable asset of any business, its data state. But data is useless if it's unreachable or insecure.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the Masterclass.
Chapter 2 to Chapter 3 Transition to Hybrid Connectivity.
Now we bridge the gap. Migrations rarely happen in a vacuum, they happen over complex, messy networks where IP addresses conflict and latency kills application performance. We shift from moving data to building the backbone that connects your legacy data center to the AWS cloud.
Chapter 3 Networking, Security, and Hybrid Architecture.
This chapter is the ultimate test of an architect's ability to handle complexity. We will navigate the overlap trap, design for zero trust, survive direct connect failures, and secure data in the most regulated environments. This is where we ensure the cloud is not just a destination, but a fortress. Scenario 31, resolving massive IP address overlap without re-IPing. Scenario 32, architecting to solve severe hybrid network latency. Scenario 33, designing redundant direct connect plus VPN connectivity. Scenario 34, surviving a primary direct connect outage mid-sync. Scenario 35, implementing zero-trust micro-segmentation in AWS. Scenario 36, migrating hardware load balancers with complex L7 rules. Scenario 37, moving SaaS apps with hard-coded IP dependencies. Scenario 38, designing for data residency with AWS local zones. Scenario 39, isolating AWS environments during an on-prem ransomware attack. Scenario 40, incident response for accidental PII exposure in S3. Scenario 41, managing executive pressure to bypass IAM security best practices. Scenario 42, transitioning 10,000 employees from on-prem AD to IAM Identity Center. Scenario 43, designing a multi-account landing zone for 50 business units. Scenario 44, translating legacy firewall rules to AWS Network Firewall. Scenario 45, deploying AWS Outposts for ultra-low latency factory floor edge cloud. Next, we solve the most common networking nightmare in hybrid cloud migrations.
Scenario 31, the overlap trap during a hybrid migration. You discover massive IP address overlapping between the on-premises data centers and the newly created AWS VPCs. How do you resolve routing without re-IPing the legacy network?
Answer: I treat this as an address abstraction problem rather than a network redesign problem. If overlapping CIDR ranges like 10.0.0.0/16 are routed directly, all traffic will black hole due to ambiguous routing decisions. I immediately implement AWS Private Link for service-level connectivity, avoiding the need for Layer 3 routing between conflicting networks. For broader communication, I deploy a private NAT gateway to translate AWS side traffic into a non-overlapping transit CIDR range that the on-prem network can recognize. This allows bidirectional communication without touching legacy IP assignments. The key insight is that IP overlap is a routing illusion, not a physical limitation. If not abstracted correctly, the migration will fail due to complete connectivity breakdown and stalled application integration. Pro tip: for full bi-directional communication, use a double NAT architecture with AWS Transit Gateway and a middle VPC. This creates a clean translation boundary that allows both environments to communicate without exposing overlapping IP spaces.
Scenario 32, applications migrated to AWS are experiencing severe latency when communicating with legacy systems still on premises. How do you architect the hybrid network to resolve this?
Answer: hybrid latency is driven by physical distance and inefficient communication patterns. You must optimize both the network path and application behavior. 1. Provision AWS Direct Connect DX with a dedicated cross-connect to replace site-to-site VPN for primary traffic. Relying on VPN adds 15 to 30 milliseconds latency, which causes synchronous application calls to time out. 2. Enable jumbo frames 9001 MTU across the Direct Connect path. Using default 1500 MTU introduces packet fragmentation, increasing latency and reducing throughput by approximately 20%. 3. Deploy AWS local zones when distance to the region exceeds 100 miles. Ignoring physical distance constraints prevents achieving sub-5 milliseconds latency requirements for real-time applications. 4. Use Application Load Balancer with HTTP/2 or gRPC to multiplex connections. Opening new TCP connections per request results in excessive handshake overhead and degraded response times. 5. Audit BGP routing paths and remove as path misconfigurations that introduce detours. For example, routing through distant regions. Suboptimal paths can double latency and degrade application performance. 6. Configure Route 53 resolver endpoints to localize DNS resolution. Routing every DNS query over hybrid links adds milliseconds per request and compounds into significant latency at scale. 7. Tune TCP window scaling on-prem servers to fully utilize high bandwidth links, for example, 10 Gbps. Without tuning, throughput collapses and applications behave as if bandwidth is severely limited. 8. Call out the failure mode explicitly. If latency is not reduced and optimized, applications will experience timeouts, degraded performance, and eventual user-facing outages, causing migration failure at the program level. Pro tip: use AWS Network Manager to visualize hybrid traffic paths. Identifying the exact hop introducing latency allows you to fix root causes instead of guessing at network issues.
Scenario 33, walk me through the exact steps to set up secure, redundant connectivity AWS Direct Connect plus site-to-site VPN backup for a massive hybrid migration.
Answer: hybrid redundancy requires deterministic failover using BGP control. Direct Connect must always be primary with VPN as fast failover. 1. Establish AWS Direct Connect with a virtual private interface (VIF) and BGP session as the primary path. Without a dedicated low latency link, large-scale migrations will suffer from unstable throughput and delays. 2. Deploy site-to-site VPN terminating on AWS Transit Gateway as the secondary path. Managing DX and VPN without a transit gateway creates complex routing tables and unreliable failover behavior. 3. Configure BGP local preference to prioritize direct connect over VPN, for example, local pref 200 versus 100. Without explicit preference, traffic may randomly prefer VPN, introducing unnecessary latency. 4. Enable bidirectional forwarding detection BFD on the DX BGP session, for example, failover detection less than 3 seconds. Without BFD, failover can take up to 90 seconds, causing session drops and data transfer interruptions. 5. Apply as path prepending on VPN routes to make them less preferred. Without path manipulation, AWS may route return traffic through the VPN, creating asymmetric routing issues. 6. Enforce encryption using ISEC for VPN and MACsec for direct connect where required. Unencrypted traffic over DX can violate compliance requirements and fail audits. 7. Set MTU correctly on VPN interfaces, for example, 1390 bytes to match encapsulation overhead. Mismatched MTU will cause packet drops during failover when traffic shifts from DX 1500 MTU to VPN. 8. Call out the failure scenario explicitly. If BGP tuning and MTU alignment are not correctly configured, failover will result in packet loss, session resets, and migration disruption, leading to program-level failure. Pro tip: perform controlled failover testing by disabling the DX link before production waves. If failover exceeds 3 seconds, your BFD or routing priorities are incorrectly configured.
Scenario 34. Halfway through replicating mission-critical data, the primary AWS Direct Connect link goes offline. How did you design your architecture to ensure resilient data transfer?
Answer: I treat this as a failover orchestration problem rather than a reactive routing issue. If failover takes longer than a few seconds, for example, greater than 3 seconds, in-flight replication sessions will drop and large transfers, for example, 10 terabytes datasets will restart, risking missed cutover windows. I rely on AWS Transit Gateway with BGP and bidirectional forwarding detection, configured to detect link failure within approximately 300 milliseconds and automatically shift traffic to the site VPN backup path. This ensures replication services like AWS DMS or data sync continue without manual intervention, even under reduced bandwidth. I also ensure MTU alignment between Direct Connect 1500 and VPN 1390 to prevent packet drops during the transition. The key insight is that resilience is engineered through pre-configured routing behavior, not manual recovery. If failover is not tuned correctly, replication will stall, forcing restart cycles and causing program-level migration delays. Pro tip: monitor BGP peer status and connection state metrics in CloudWatch. Early detection of link degradation allows proactive validation of failover readiness before a full outage occurs.
Scenario 35. A government agency requires a strict zero-trust architecture. How do you enforce micro-segmentation and strict access controls during the transition phase from a flat on-prem network?
Answer: zero trust requires eliminating implicit trust boundaries and enforcing identity-based access at every layer during migration. 1. Implement AWS VPC Lattice to enforce service-to-service access using IAM-based authentication. Relying on sitter-based security groups alone allows lateral movement if a single instance is compromised. 2. Deploy AWS Network Firewall for deep packet inspection of all ingress and egress traffic. Without Layer 7 inspection, malicious payloads from on-prem systems can bypass basic network controls. 3. Enforce IAM least privilege with condition-based policies tied to VPC endpoints. Allowing unrestricted access paths enables credential misuse and unauthorized data access. 4. Enable VPC flow logs and integrate with Amazon Guard Duty for anomaly detection, for example, unexpected port scanning or data exfiltration patterns. Without monitoring, compromised instances will operate undetected. 5. Replace SSH access with AWS Systems Manager Session Manager to eliminate open ports, for example, port 22. Maintaining traditional SSH access exposes a major attack surface. 6. Use prefix lists to centrally manage allowed CIDR ranges across multiple security groups. Manual rule updates introduce configuration drift and inconsistent enforcement. 7. Continuously validate segmentation using automated checks, for example. No cross-tier access beyond defined policies. Failing to validate allows silent policy violations to accumulate. 8. Call out the failure mode explicitly. If zero trust controls are not enforced, a compromised on-prem system can laterally move into AWS and encrypt or exfiltrate critical workloads, causing full environment compromise and program-level failure. Pro tip: use security group referencing instead of IP-based rules. This ensures segmentation policies remain intact even as instances scale or IPs change during migration.
Scenario 36. An application relies on legacy hardware load balancers with incredibly complex, hard-coded Layer 7 routing rules. How do you translate and migrate these to AWS application load balancers?
Answer: this is a rule parity and evaluation order problem. You must replicate L7 behavior deterministically before cutover to avoid routing drift. 1. Export and normalize all L7 rules from the hardware LB into a canonical rule set, for example, 500 to 2000 rules with explicit priority ordering. Failing to preserve evaluation order will route traffic to incorrect backends and break application flows. 2. Map host/path/header conditions to ALB listener rules priority 1 to 1000 and validate limits, for example, rule quotas per listener. Exceeding limits without consolidation will cause deployment failures and incomplete rule coverage. 3. Translate, rewrite/redirect logic using ALB actions and AWS WAF for advanced conditions. Omitting rewrite parity will change request URIs and cause downstream service mismatches. 4. Externalize sticky sessions to application or use ALB target group stickiness with defined duration, for example, 300 to 3600 seconds. Ignoring session affinity breaks stateful user flows during migration. 5. Implement weighted target groups for canary cutover, for example, 90/10 to 50/50 to 0/100. Performing a Big Bang switch risks widespread outages if rule parity is incomplete. 6. Recreate health checks with exact paths/timeouts, for example, interval 10 seconds, timeout 5 seconds, healthy threshold 3. Mismatched health checks will mark healthy targets as unhealthy and drop traffic. 7. Enable access logs and compare against legacy logs, for example, sample 5 to 10% traffic to verify routing equivalence. Skipping validation allows silent misroutes to reach production. 8. Call out the failure mode explicitly. If rule ordering, rewrites, and health checks are not matched precisely, traffic will be misrouted or dropped at scale, causing user-facing outages and program-level migration failure. Pro tip: build a rule translation test harness that replays production requests against ALB and a staging VPC and diffs responses against the legacy LB. Catching a single mismatched rule early can prevent cascading failures at cutover.
Scenario 37. A SaaS application slated for migration has hard-coded IP addresses deeply embedded in its microservices. What is your migration plan to move this to AWS without rewriting the codebase?
Answer: this is an address abstraction problem. You must preserve expected endpoints while decoupling actual service locations. 1. Introduce a DNS abstraction layer using Amazon Route 53 and replace reachable IP endpoints with stable hostnames via split horizon DNS. Failing to abstract endpoints forces code changes and blocks migration timelines. 2. Deploy network load balancers with static IPs, for example, 2 to 3 elastic IPs per Z to front backend services. Without stable ingress points, hard-coded dependencies will fail immediately after cutover. 3. Implement a transparent proxy or NAT translation layer to map legacy IPs to new service endpoints. Without translation, inter-service calls will break due to unreachable addresses. 4. Use AWS Private Link for service exposure across VPCs. while preserving endpoint consistency. Relying on direct IP connectivity across environments introduces routing conflicts and brittle dependencies. 5. Leverage VPC routing and prefix lists to redirect legacy IP ranges to proxy endpoints. Missing centralized routing control leads to inconsistent behavior across services. 6. Implement phased cutover with traffic shifting, for example, 20% to 50% to 100% through DNS or load balancer weighting. A full cutover risks complete application failure if mappings are incomplete. 7. Continuously validate service reachability and response parity, for example, 99.9% success rate baseline before progressing phases. Skipping validation allows silent failures to propagate. 8. Call out the failure mode explicitly. If IP abstraction and translation are not implemented correctly, hard-coded dependencies will break at runtime, causing cascading service failures and program-level migration collapse. Pro tip: capture all outbound connections using VPC flow logs before migration to build a definitive dependency map. Hard-coded IPs often exist in unexpected paths, and missing even one can break critical workflows.
Scenario 38. A pharmaceutical company dictates that certain sensitive data components cannot legally leave a specific geographic city. How do you architect an AWS local zone solution to satisfy this during migration?
Answer: this is a data residency enforcement problem. You must physically anchor regulated components in city, while enabling controlled interaction with regional services. 1. Deploy the regulated workloads in an AWS local zone within the mandated city, and place databases, for example, RDS on local zone subnets or EC2 hosted DB there. Moving these components to the parent region violates residency and fails compliance audits. 2. Enforce data boundary controls using service control policies (SCPs) to deny cross-region data movement for tagged resources. Without SCP guardrails, engineers can accidentally replicate or snapshot data to out-of-city regions. 3. Use VPC endpoints private link and keep all service-to-service traffic private between local zone and region. Exposing traffic over public endpoints risks data egress outside the allowed geography. 4. Implement encryption with AWS KMS keys scoped to the local zone/region and strict key policies. Misscoped keys can allow decryption outside the approved boundary and breach compliance. 5. Design data flows so only non-sensitive, aggregated data leaves the local zone, for example, less than 1% of total dataset. Sending raw PII upstream increases legal exposure and audit risk. 6. Use asynchronous replication or APIs to share derived datasets to the region with explicit allow lists. Direct database replication of sensitive tables outside the city breaks residency constraints. 7. Validate residency continuously using AWS config rules, for example. Deny resources in non-approved locations and cloud trail data events. Without continuous validation, drift will silently move data out of compliance. 8. Call out the failure mode explicitly. If data residency controls are not strictly enforced, sensitive data can leave the city boundary, resulting in regulatory violations, legal penalties, and program-level migration failure. Pro tip: tag all regulated resources with a residency equals city name key and enforce SCP conditions on that tag. This creates a simple, auditable control that blocks accidental cross-region operations at scale.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Scenario 39. Right in the middle of a major migration wave, the client's on-premises environment is hit by a ransomware attack. How do you isolate the AWS environment and verify the integrity of already migrated data?
Answer: I treat this as an immediate containment and trust verification problem, not a migration problem. If hybrid connectivity remains active for even a few minutes, ransomware can traverse into AWS and compromise already migrated workloads, turning a localized incident into a full cloud breach. I immediately sever all hybrid links by disabling Transit Gateway attachments and VPN tunnels, enforcing isolation within less than 5 minutes to contain blast radius. I halt all replication pipelines such as AWS DMS and data sync to prevent ingestion of encrypted or corrupted data. I then validate migrated datasets using checksum verification and DMS validation against last known good snapshots, prioritizing 100% validation for critical systems. Any discrepancy triggers restoration from immutable backups such as S3 object lock or version snapshots. The key insight is that migration must stop the moment trust is broken. If containment and validation are delayed, ransomware propagation or silent data corruption will force full rollback and cause program-level failure. Pro tip: maintain an isolated recovery account with cross-account immutable backups. If your primary AWS account is ever compromised, this ensures a guaranteed clean recovery point.
Scenario 40. During the migration of a database, sensitive PII data was accidentally exposed in an unencrypted S3 bucket. What are your immediate incident response and long-term remediation steps?
Answer: I treat this as a live data breach scenario where every minute of exposure increases regulatory and legal risk. If the bucket remains exposed, even briefly, unauthorized access can occur and escalate into reportable data breach incidents. I immediately block all public access and remove open bucket policies, ensuring exposure is contained within minutes less than 10 minutes. I enforce encryption using SSCKMS and reprocess 100% of objects to eliminate any residual unencrypted data. I audit CloudTrail and S3 access logs to determine if unauthorized access occurred and identify affected data scope. Based on findings, I initiate mandatory breach notification workflows aligned with compliance requirements. Long-term, I enforce guardrails using AWS config rules and SCPs to prevent creation of unencrypted or publicly accessible buckets. The key insight is that prevention must be automated, not procedural. If controls rely on manual enforcement, the same failure will recur and result in regulatory penalties and program-level impact. Pro tip: enable block public access and enforce encryption via bucket policy at the account level. This removes the possibility of accidental exposure during high-speed migration activities.
Scenario 41. The client's leadership wants to migrate at lightning speed and asks you to temporarily ignore IAM best practices and open security groups to 0.0.0.0/0 to just get it working. How do you handle this?
Answer: I treat this as a risk containment and governance enforcement problem, not a delivery acceleration request. Opening security groups to 0.0.0.0/0, even temporarily, exposes critical workloads to the entire internet within minutes and can lead to immediate exploitation, especially during migration when systems are least hardened. I do not accept the request as is. Instead, I provide a controlled alternative by implementing time-bound access using AWS Systems Manager Session Manager and temporary scope security group rules restricted to known IP ranges, for example, /32 access for specific engineers. I enforce guardrails using service control policies and AWS config rules to prevent any unrestricted exposure from being deployed, even under executive pressure. I also quantify the risk in business terms, demonstrating that a single breach can delay the migration by weeks due to incident response and compliance impact. The key insight is that speed without control is not acceleration, it is risk multiplication. If this is not enforced, the migration can trigger a security incident that halts the entire program. Pro tip: implement an automated break glass access workflow with strict logging and auto expiry, for example, 1-hour access window. This gives leadership the perception of speed while maintaining full security control and auditability.
Scenario 42. A client wants to completely abandon their on-premises Active Directory for a cloud-native identity model. How do you manage the cutover for 10,000 users?
Answer: ripping out on-prem AD is the highest risk move in enterprise IT. You must decouple AWS authentication from legacy protocols without causing a day-one lockout cascade. 1. Establish the new source of truth in IAM Identity Center or via a cloud IDP like Entra ID using SIM. Attempting a big bang cutover without an automated identity sync pipeline will orphan thousands of users the moment the legacy domain controllers are shut down. 2. Map legacy AD security groups directly to AWS permission sets rather than assigning users individually. Mapping 10,000 individual users manually will instantly breach IAM Identity Center quota limits and create an unmanageable governance nightmare. 3. Address the developer CLI trap immediately. Mandate the rollout of AWS SSO login configurations to all engineering laptops. Severing AD instantly breaks legacy federated CLI tools, which will silently halt local development and CI and CD pipelines. 4. Execute an aggressive MFA re-enrollment campaign in the new cloud directory weeks prior to cutover. Assuming legacy on-prem MFA hardware tokens will automatically translate to the new cloud, IDP guarantees 10,000 day one help desk tickets. 5. Mitigate the legacy protocol trap by spinning up AWS-managed Microsoft AD to handle lingering NTLM/Kerberos requests. Hard killing on-prem AD without a cloud-based LDAP fallback will instantly brick legacy intranet apps and Windows file shares. 6. Configure a shadow login testing phase. Route a 5% pilot group of cross-department users to the new SSO portal to validate application claims. Skipping this phase allows silent SAML assertion mismatches to reach production. 7. Monitor authentication latency and throttling exception metrics in Cloud Trail during the 8 a.m. Monday login spike. A cloud-native identity model must be pre-warmed, otherwise the concurrent login storm will trigger API rate limits and lock out the company. Pro tip: do not leave the IAM Identity Center session duration at the default 1 hour during the cutover week. Set it to 8 or 12 hours. If 10,000 users are forced to re-authenticate 8 times a day while learning a new SSO system, user frustration will derail the entire migration's perceived success.
Scenario 43. An enterprise with 50 distinct business units needs to migrate into AWS. How do you design a multi-account landing zone using AWS Control Tower and AWS organizations?
Answer: setting up a 50 BU landing zone isn't just creating accounts, it's architecting strict blast radius and billing boundaries to prevent organizational chaos. 1. Deploy AWS Control Tower to vend and govern the accounts automatically. Manually creating 50+ AWS accounts leads to disjointed cloud trail logging, identity drift, and an immediate failure of compliance audits. 2. Structure organizational units OUs by environment lifecycle, for example, prod versus non-prod across 50 BUs, not by the HR org chart. Applying strict production service control policies SCPs to an org chart OU will inadvertently brick their development sandboxes. 3. Centralize ingress and egress through an AWS Transit Gateway in a dedicated network hub account handling 50+ VPC attachments, allowing each BU to spin up its own internet gateway, creates an unauditable perimeter that InfoSec cannot defend. 4. Implement AWS Resource Access Manager RAM to share core subnets across dozens of accounts, forcing every BU to manage their own VPC peering mesh hits AWS peering limits, approximately 125 per VPC, and creates routing spaghetti that collapses under scale. 5. Apply SCPs at the root level to explicitly deny region creation outside approved geographic zones, for example. Allow only 2 to 3 regions. Without this, a compromised developer token can spin up large compute fleets in unmonitored regions within minutes. 6. Configure AWS IAM Identity Center with attribute-based access control ABAC across 50+ accounts. Hard-coding IAM roles per BU exceeds policy size limits and becomes operationally unmanageable. 7. Automate account vending using Account Factory for Terraform AFT with standardized baselines, for example, less than 15-minute account provisioning. Manual control tower provisioning introduces drift that only surfaces during production cutovers. 8. Unstructured account sprawl without enforced guardrails across 50 business units leads to security gaps, uncontrolled spend, and audit failures that require months of re-architecture to recover. Pro tip: use AWS cost categories and SCPs to mandate billing tags upon account creation. Deny EC2:run instances. If cost center tags are missing, this enforces FinOps discipline before the first dollar is spent.
Scenario 44. How do you ensure that complex legacy firewall rules and network security groups (NSGs) are properly translated to AWS security groups and network ACLs without introducing vulnerabilities?
Answer: translating legacy firewalls is a paradigm shift from perimeter-based IP filtering to identity-based micro-segmentation. You cannot do a one-to-one copy-paste. 1. Abandon network-wide subnet IP rules in favor of AWS security groups attached to Elastic Network Interfaces (ENIs). Forcing a legacy perimeter model using network ACLs hits the hard limit of 20 rules, breaking complex application traffic instantly. 2. Consolidate redundant IP rules using AWS managed prefix lists, for example, collapsing 500+ CIDR into shared objects. Manually translating each block into security group rules exceeds the 60 rule quota per SG and fails deployment. 3. Deploy AWS Network Firewall for Deep Packet Inspection (DPI) at the edge. Relying only on security groups allows malicious Layer 7 payloads to pass unchecked, bypassing controls that legacy appliances enforced. 4. Translate stateful behavior correctly. Duplicating both inbound and outbound rules from legacy firewalls into security groups creates unnecessary policy bloat and increases the chance of misconfiguration. 5. Implement security group referencing, for example, allowing traffic from SG app instead of fixed CIDR. Relying on static IP rules breaks auto-scaling workloads where instance IPs change dynamically. 6. Audit legacy any outbound rules and restrict egress, for example, limit to required ports and destinations. Copying unrestricted egress into AWS exposes instances to data exfiltration and SSRF attack paths. 7. Validate rule translation using AWS VPC Reachability Analyzer across critical paths, for example. Validate 100% of tier-to-tier flows. Skipping validation allows broken paths to surface only under live production traffic. 8. Improper rule translation or missed dependencies will silently block or expose traffic paths, leading to partial outages, security gaps, and production incidents that are extremely difficult to trace post-migration. Pro tip: build a rule diff matrix mapping legacy firewall rules to AWS constructs before implementation. This ensures every rule has a deliberate equivalent and prevents accidental over permissive configurations.
Scenario 45. A manufacturing company wants to run ultra-low latency workloads on the factory floor while migrating their central management systems to the cloud. How do you design a hybrid edge to cloud architecture using AWS Outposts?
Answer: Factory floors are bound by the laws of physics. When a robotic arm requires sub-millisecond response times, you must bring the cloud to the edge. 1. Deploy AWS Outposts directly in the factory data center to anchor critical manufacturing execution systems, MES. Migrating these directly to the AWS region introduces a 20 milliseconds plus latency penalty that will physically crash high-speed assembly line robotics. 2. Architect the Outpost Local Gateway, LGW, to route traffic directly to the local factory LAN. If you accidentally route local machine-to-machine traffic through the service link back to the parent AWS region, you introduce the exact latency you paid Outposts to avoid. 3. Design for disconnected survivability by ensuring local factory workloads do not rely on regional AWS IAM or Route 53 resolvers. If the fiber link to the parent region goes down, applications requiring regional API calls will freeze the factory floor. 4. Migrate the central telemetry, analytics, and ERP systems to the parent AWS region. Keeping heavy analytics on the Outpost consumes its finite local compute capacity, starving the critical low-latency robotic workloads. 5. Enforce data synchronization using AWS Data Sync or S3 replication. The Outpost must continuously flush non-critical telemetry data to the parent region. Otherwise, the local EBS/S3 storage will hit 100% capacity and halt local production. 6. Size the Outpost rack with N+1 compute capacity for high availability. Unlike an AWS region where EC2 capacity is virtually infinite, an Outpost is a physical rack. If a blade fails and you have no buffer, your factory application goes down hard. 7. Anchor the Outpost to the closest physical AWS region via an active/active direct connect setup. Relying on a standard internet VPN for the service link introduces unacceptable jitter to the Outpost control plane synchronization. Pro tip: use AWS IoT greengrass on smaller edge gateways attached to the individual assembly machines, feeding into the centralized AWS Outposts rack. This provides an additional layer of local compute filtering, so you do not overwhelm the Outposts network with raw, unfiltered vibration sensor data.
Chapter 3 Conclusion.
You have successfully navigated the hybrid network minefield. By abstracting overlapping IP addresses, enforcing zero-trust micro-segmentation, and defending the perimeter during active ransomware attacks, you have proven that you can secure the bridge between on-premises and the cloud.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Chapter 3 to Chapter 4, Transition to the Cutover.
Planning is over. The architectural diagrams are signed off. It is now 2 a.m. on a Sunday, the maintenance window is open, and production traffic is being shifted. This is where theory ends and reality begins. Welcome to the execution phase.
Chapter 4, Execution and Cutover Nightmares.
This chapter is built entirely on war stories. We will tackle MGN replication failures, split-brain database crises, global DNS caching nightmares, and mid-sync power outages. This is how top-tier architects survive the weekend and save the migration. Scenario 46, architecting a zero-downtime cutover for 24/7 logistics. Scenario 47, the 15-minute panic MGN target instance failure. Scenario 48, disaster recovery for a split-brain inconsistent state. Scenario 49, the DNS nightmare delayed propagation and data divergence. Scenario 50, forcing traffic over deep ISP caching 3 days post-cutover. Scenario 51, immediate fixes for broken third-party API IP whitelists. Scenario 52, hitting hard limitations with third-party migration tools. Scenario 53, overcoming client trust issues around automated tools. Scenario 54, handling undocumented dependencies discovered mid-cutover. Scenario 55, troubleshooting production-scale failures post-staging. Scenario 56, global streaming blue-green deployment architecture. Scenario 57, the 2-hour post-cutover validation framework. Scenario 58, seamlessly migrating Apache Kafka to Amazon MSK. Scenario 59, salvaging migration timelines after complete on-prem power loss. Scenario 60, resolving legacy Windows 2008 EC2 compatibility crashes. Next, we enter the war room and tackle the highest pressure cutover scenarios.
Scenario 46, a global logistics platform operates 24/7. Even a 1-minute outage leads to massive financial loss. Architect a completely invisible, zero-downtime cutover.
Answer: a zero-downtime cutover is not a migration. It is an active/active distributed systems problem. You must decouple the data layer from the application layer to buffer transactions during the switch. 1. Establish an active data layer using bidirectional AWS DMS replication. Relying on a one-way sync guarantees catastrophic data loss if a severe application bug forces you to roll back to on-premises after cutover. 2. Decouple the front-end ingestion using Amazon SQS or Amazon MQ to buffer incoming logistics payloads. Without a message queue holding the requests, the 10-second database endpoint swap will result in dropped 503 errors for active customers. 3. Implement Amazon Route 53 weighted routing at 99/1 ratio to bleed traffic to the AWS environment. Executing a Big Bang DNS switch for a global platform instantly overwhelms cold cloud caches and crashes the new target instances. 4. Validate database read replicas in AWS with synthetic traffic before the right cutover. Failing to warm up the Aurora buffer cache means the new primary database will hit a 100% CPU lockup the moment live traffic hits it. 5. Shift read-only traffic to AWS first to validate network paths and application behavior. Offloading select queries proves your IAM roles and security groups work under load without risking the mutation of critical data. 6. Execute the right cutover at the application connection pool level, not DNS. DNS-TTLs are unreliable, but dynamically updating the backend JDBC/ODBC connection strings forces an immediate and deterministic shift to the AWS database. 7. Call out the failure mode explicitly. If you fail to drain long-running and flight transactions before shifting the endpoint, active database locks will break. Corrupting live inventory states across the global supply chain. Pro tip: use AWS Global Accelerator for the front-end cutover. It provides 2 static unicast IPs that route directly to your ALB. Because the IPs never change, you bypass the global DNS-TTL propagation nightmare entirely, allowing you to dial traffic from on-prem to AWS instantaneously.
Scenario 47, The 15-minute panic: you are executing a cutover using AWS Application Migration Service (MGN). 15 minutes into the cutover window, target EC2 instances fail health checks. Walk me through your immediate rollback steps.
Answer: your rollback window expires in exactly 20 minutes, and the target AWS instances are sitting at 1/2 status checks failed. At this exact moment, attempting to SSH or RDP into broken servers to debug boot drivers is a trap that will burn your remaining time and force an extended outage. I immediately declare a rollback, pausing the cutover sequence and instructing the networking team to repoint the global load balancers back to the on-premises environment. Once the bleeding is stopped and user traffic is stabilized, I pull the EC2 system logs and instance console screenshots. The failure is almost always missing Nitro hypervisor drivers, unmatched ENI attachments, or a legacy kernel panic during boot. The key insight is that a rollback is not a failure, it is the successful execution of your continuity plan. Troubleshooting a broken OS mid-cutover turns a controlled delay into a resume-generating outage. Pro tip: never skip the MGN test instance phase. Launching a test instance 48 hours before the actual cutover catches the dreaded Linux kernel panic or Windows blue screen caused by missing AWS drivers, while you still have days to inject them on premises.
Scenario 48. A migration fails halfway through the weekend maintenance window, leaving systems in a split-brain, inconsistent state. What is your disaster recovery plan?
Answer: half of your users successfully resolved the new DNS and are writing to the AWS RDS database, while the other half are stubbornly hitting the legacy on-premises SQL cluster. If you let this run for even another 10 minutes, you will spend weeks manually reconciling corrupted financial ledgers. I instantly sever the hybrid network link and lock the AWS security groups to kill all inbound application traffic on both sides, forcing a hard global outage. An explicit outage is infinitely better than silent data corruption. I use the database transaction logs to identify the exact timestamp of the split, extract the Delta records from AWS, and script a manual replay into the on-premises database to achieve a unified state before bringing the legacy system back online. The key insight is that in a split-brain crisis, your priority is state preservation, not uptime. Pro tip: before any database cutover, configure the on-premises database to read-only mode at the application or DB engine level right before the DNS flip. This physically prevents a split-brain scenario from ever occurring, because even if DNS propagation fails, users cannot write to the old database.
Scenario 49. The DNS nightmare during final cutover: DNS propagation is delayed. Users are inconsistently hitting both the old on-premises system and the new AWS system. How do you handle this?
Answer: global ISP DNS servers are ignoring your 60-second TTL, and thousands of customers are continuing to route to the old legacy IP address. If you shut down the on-premises servers right now, you will drop active shopping carts and trigger a massive SEV1 incident. Instead of waiting for the internet to catch up, I leave the on-premises environment running, but immediately replace its application layer with a reverse proxy like Nginx or HA proxy. This proxy catches the ghost traffic hitting the old IP and transparently forwards it over the AWS Direct Connect link to the new AWS Application Load Balancer. The legacy users experience slightly higher latency, but zero dropped requests. The key insight is that you cannot control global ISP caching behavior, so you must architect your legacy environment to act as a fail-forward router during the cutover. Pro tip: do not tear down the reverse proxy until you review its access logs and confirm traffic has dropped to absolute zero. Some legacy B2B API partners hardcode IP addresses and bypass DNS entirely. The proxy logs will reveal exactly who they are so you can force them to update their code.
Scenario 50. Full migration is complete, but 3 days later you discover some global users are still accessing the old on-premises system due to deep ISP caching issues. How do you force traffic to AWS?
Answer: it's Wednesday. The migration was declared successful on Sunday, But database drift alerts are firing because an isolated pocket of users in Europe is still somehow hitting the legacy on-prem infrastructure. Shutting off the legacy edge routers now will sever critical API clients who ignored your DNS updates. I immediately deploy an IP-level NAT translation on the legacy on-premises edge firewall, forcefully forwarding all traffic destined for the old public IP directly to the new AWS Elastic IP over the Internet. This permanently bridges the gap for non-compliant clients while centralizing all rights to the cloud database, stopping the drift. The key insight is that a migration is not finished when the DNS updates propagate. It is finished when the legacy network captures 0 packets. Pro tip: capture the X forwarded for headers on your AWS load balancer for the NAT traffic. This gives you the exact source IP addresses of the stubborn clients whose local DNS is broken, allowing your support team to contact them directly and enforce a cache flush on their end.
Scenario 51. A third-party API deeply integrated into your application breaks immediately after migration because it strictly whitelists your old on-premises IP addresses. How do you fix this fast?
Answer: the cutover was flawless, but payment processing is completely dead because a critical third-party vendor strictly whitelists your old on-premises NAT IP address. The vendor's SLA to update IP whitelists is 5 business days, and you are losing revenue by the second. I do not attempt to rewrite the application code to bypass the gateway or beg the vendor for an expedited ticket. I immediately configure the AWS Transit Gateway to route outbound traffic for that specific vendor's sitter block back down the direct connect link to the legacy on-premises NAT gateway. The traffic exits the legacy data center using the old, approved IP address, completely bypassing the vendor's block. The key insight is that in cloud migrations, hybrid networking is not just for moving data inward, it's an emergency escape hatch for outbound legacy dependencies. Pro tip: avoid this nightmare entirely by requesting a bring your own IP BYOIP transfer to AWS weeks before the cutover. By moving your legacy public/24 subnet to AWS, you assign your exact old IP addresses to your AWS NAT gateways, neutralizing third-party whitelist issues before they happen.
Scenario 52. Your team started migrating using a specific third-party migration tool, but mid-project, you hit hard technical limitations. How do you decide whether to switch to native AWS tools or build workarounds?
Answer: you are 60% through your server waves, but your expensive third-party block replication agent crashes every night because it cannot handle the I/O churn of your massive transactional databases. If you keep forcing it, you will miss your cutover window and burn out your engineering team on daily troubleshooting. I do not attempt to hack the vendor's tool or wait on a feature request. I surgically pivot the architecture. I keep the third-party tool for the stateless web and application tiers where it works reliably, but I immediately carve out the heavy databases and cut them over using native engine tools like Oracle Data Guard, SQL Server Always On, or AWS DMS. The key insight is that tool loyalty in a migration is a trap. You must treat migration tools as disposable conduits, selecting the exact physical mechanism that matches the workload's I/O profile. Pro tip: when running a multi-tool migration, use AWS Migration Hub as your single pane of glass. It integrates with both native tools like MGN and DMS and third-party partner tools, preventing you from losing visibility when tracking a hybrid cutover strategy.
Scenario 53. A strict client insists on using slow, manual server rebuilds instead of automated block-level replication tools like MGN due to trust issues. How do you handle this objection?
Answer: the CISO is blocking your automated migration, demanding that every server be rebuilt from scratch via configuration management, because they refuse to lift and shift legacy, OS rot, and hidden malware into their pristine cloud. Arguing about migration velocity here is useless. They care about risk, not speed. I validate their security concern but reframe the solution. I deploy AWS Application Migration Service, MGN, to perform the rapid block-level lift, but I attach an AWS Systems Manager SSM post-launch action to every target instance. The moment the server boots in AWS, SSM automatically runs a hardened Ansible playbook, installs CrowdStrike, executes an AWS Inspector vulnerability scan, and isolates the VPC until the scan passes. The key insight is that security teams do not actually hate lift and shift automation. They hate inheriting an unverified state. When you wrap the migration in a cryptographic security pipeline, you win their trust. Pro tip: show the CISO the AWS MGN launch template configurations. By proving you can automatically strip away legacy public IPs, detach unencrypted EBS volumes, and force IMD SV2 on the instances before they even boot in AWS, you turn the migration tool into a security enforcement mechanism.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the Masterclass.
Scenario 54. During the final hours of a migration cutover, you discover a critical, undocumented legacy dependency that is blocking the app from starting. What do you do?
Answer: you are 30 minutes away from signing off on the cutover when the application crashes on boot. The logs reveal a hard-coded TCP connection to an undocumented S400 mainframe sitting in a closet back on premises. If you roll back now, you burn the entire weekend, and the business loses faith. I do not attempt to rewrite the application code or rush a mainframe migration mid-flight. I immediately build a network bridge. I configure the AWS Transit Gateway to route that specific legacy IP subnet back down the direct connect link. I deploy an AWS Route 53 outbound resolver to spoof the legacy hostname, tricking the cloud application into thinking the mainframe is sitting right next to it in the VPC. The key insight is that migrations are not about achieving perfect isolation on day one. They are about keeping the application alive. Hybrid networking is your ultimate emergency escape hatch. Pro tip: check the VPC flow logs for the newly migrated EC2 instance immediately after it boots. Filter for reject actions on destination ports like 23 Telnet or 1433 SQL. This will instantly expose any undocumented legacy systems the application is desperately trying to reach, allowing you to punch the exact firewall holes required to save the cutover.
Scenario 55. A migrated workload performed flawlessly in the staging/testing phase on AWS, but fails immediately in production due to massive differences in user scale. How do you troubleshoot?
Answer: the application passed UAT with flying colors, but 10 minutes into the live cutover, thousands of global users hit the endpoint and the database CPU pegs to 100%, taking the system down. Scaling up the RDS instance size will take 15 minutes you do not have, and it will not fix the core issue. I look past compute and check the database connections metric. Staging tests functionally validate code, but they rarely simulate connection storms. The legacy hardware load balancer used to multiplex connections, but the new AWS architecture is spawning thousands of raw, unpooled TCP connections, exhausting the database memory. I immediately deploy Amazon RDS proxy in front of the database to pool and share connections, absorbing the storm without requiring a single application code change. The key insight is that staging environments test functionality, but only production tests physics. You must architect for connection exhaustion, not just compute limits. Pro tip: an AWS application load balancer ALB scales automatically, but not instantly. If you anticipate a massive 0 to 100,000 user spike the second you flip DNS, open a ticket with AWS support 48 hours prior to pre-warm the ALB. Otherwise, the ALB will drop legitimate user traffic with 503 errors while it frantically tries to scale out.
Scenario 56. A global streaming service needs to migrate backend services while keeping the frontend live globally. Walk me through your blue-green deployment strategy.
Answer: a global zero-downtime cutover requires abstracting the network layer and decoupling the session state so you can shift traffic deterministically. 1. Externalize all user session state to Amazon Elasticache Redis or DynamoDB before the cutover. Attempting a blue-green shift within memory sessions will instantly log out millions of streaming users the moment traffic shifts to the new AWS environment. 2. Deploy AWS Global Accelerator instead of relying purely on DNS. Global Accelerator provides two static Anycast IPs, allowing you to use endpoint weights to instantly dial traffic from on-prem to AWS without waiting hours for global ISP DNS caches to clear. 3. Establish a dual-write pipeline for the backend databases. Use a message broker like Amazon MSK or SQS to replicate live user watch history to both the old and new databases simultaneously, ensuring data parity regardless of which environment the user hits. 4. Configure application load balancer ALB listener rules for canary routing. Use HTTP header-based routing to quietly send internal queue engineers to the green AWS environment in production before shifting a single real customer. 5. Implement a 10% canary shift and hold for 15 minutes. Monitor the 500-level error rate and latency metrics exclusively for the green target group, automatically triggering an AWS Lambda rollback function if errors exceed a 1% threshold. 6. Ensure auto-scaling groups in the green environment are pre-scaled to 100% of expected peak capacity. A common failure is shifting traffic to a minimum capacity AWS environment that crashes before auto-scaling has time to react. 7. Call out the failure mode explicitly. If you execute a blue-green cutover on a global scale without a bi-directional data sync, rolling back due to an AWS application failure will instantly corrupt all user data generated during the shift window. Pro tip: use Amazon CloudFront's continuous deployment feature. It allows you to shift a percentage of live CDN traffic to a staging distribution natively at the edge, entirely bypassing backend DNS complexity.
Scenario 57. Exactly how do you validate application functionality, performance parity, and data integrity in the crucial 2 hours post-cutover before you inform the business?
Answer: the post-cutover window is a race against data divergence. You must mathematically prove the environment is sound before users generate new state. 1. Execute automated AWS synthetics canaries to crawl the application's critical paths, for example, login, checkout. Relying on manual queue, clicking through the UI is too slow and misses subtle edge case API failures. 2. Validate database integrity using AWS DMS row count and checksum validation tools. Comparing file sizes is useless. You must hash the source and target tables to definitively prove zero data corruption occurred during the final delta sync. 3. Compare P90 and P99 API latency metrics against the on-premises baseline captured last week. If the AWS application returns 200 OKs, but takes 4 times longer to process queries, it is a performance failure that will crash under peak load. 4. Run VPC Reachability Analyzer across all newly migrated subnets. This mathematically proves that the exact security groups and NSC else required for third-party API communication are open, without having to send actual test payloads. 5. Audit the AWS Cloud Trail logs for access denied errors across the newly migrated IAM roles. An application might appear healthy, but silently fail to write background telemetry or backups due to missing KMS or S3 permissions. 6. Verify the point of no return triggers. Define the exact condition, for example, first live customer transaction, where a rollback to on-premises is no longer possible without a massive data reconciliation project. 7. Call out the failure mode explicitly. If you declare success based purely on pinging the web server, you will likely discover 24 hours later that the nightly batch jobs are crashing due to hard-coded legacy IPs, forcing a humiliating SEV1 outage. Pro tip: inject test orders using a dedicated queue account right after cutover, and immediately check your AWS billing/invoicing integrations. If the web tier works but the payment gateway webhook is blocked by an AWS security group, the business is offline even if the website is up.
Scenario 58. You have migrated an on-premises Apache Kafka cluster to Amazon MSK. How do you seamlessly redirect producer and consumer traffic without dropping a single message?
Answer: Kafka migrations are all about offset management. You cannot simply flip a DNS switch. You must synchronize the logs and translate consumer state. 1. Deploy MirrorMaker 2.0 to continuously replicate topics, configurations, and consumer group offsets from the on-premises cluster to Amazon MSK. Attempting manual data dumps will result in dropped messages and out-of-order event streaming. 2. Pause the application consumers first, allowing them to finish processing in-flight messages. If you redirect producers before pausing consumers, you will create a race condition where messages are processed out of order across the two clusters. 3. Utilize the MirrorMaker 2 offset translation feature. Because offsets message IDs in the new MSK cluster will not exactly match the legacy cluster. Failing to translate them will cause your consumers to reprocess millions of old messages or skip new ones entirely. 4. Redirect the producers to the MSK brokers and monitor the bytes in per sec metric, ensuring producers are successfully writing to AWS before reconnecting consumers guarantees you do not drop real-time ingestion. 5. Restart the consumers pointing to the MSK cluster. They will use the translated offsets to pick up exactly where they left off, ensuring exactly once or at least once processing parity. 6. Maintain the MirrorMaker 2 pipeline in reverse MSK back to on-premises for 48 hours. If you discover a critical application bug and must roll back, this reverse sync ensures the legacy cluster has all the new cloud-generated events. 7. Call out the failure mode explicitly. If you fail to configure identical partition counts and replication factors in MSK, your highly tuned producer applications will throw timeout exceptions and drop critical data payloads. Pro tip: during the sync phase, consumer offsets in MSK will appear as lagging because MirrorMaker replicates data slightly faster than it commits offsets. Do not panic and manually reset the consumers. Wait for the final cutover drain. The offsets will catch up and align perfectly.
Scenario 59. An unexpected, complete power outage occurs in the on-premises data center halfway through your AWS data replication sync. How do you salvage the migration timeline?
Answer: a blown transformer takes out the entire legacy facility, hard crashing the source servers right in the middle of your block-level sync. You have 48 hours to get the business back online, but the on-prem SN is completely corrupted. At this point, the migration is officially a disaster recovery event. I do not wait for the facility to restore power. I immediately trigger an aggressive failover using AWS Application Migration Service (MGN). Because MGN maintains continuous, sub-second block-level replication, I launch the target EC2 instances in AWS from the most recent crash-consistent snapshot, taken milliseconds before the power failure. I force a disk consistency check, FSCK/CHKDSK on boot, to repair any in-flight transaction corruption caused by the hard crash. We then manually update Route 53 to point to the new AWS environment. The key insight is that modern block-level migration tools are identical to disaster recovery engines. You salvage the timeline by cutting over to the cloud early, abandoning the dead data center entirely. Pro tip: EC2 instances launched from crash-consistent state might have corrupted database transaction logs. Keep a runbook ready detailing how to forcefully recover SQL Server or Oracle from a dirty shutdown state. Knowing the exact DBCC commands to repair a torn page is what turns a dead database into a live cloud asset.
Scenario 60. You encounter severe application compatibility issues when rehosting legacy Windows Server 2008 instances to EC2. How do you resolve this while keeping the migration on track?
Answer: you've successfully replicated a mission-critical Windows Server 2008 R2 instance via AWS MGN. But upon launch, it instantly throws a blue screen of death BSOD with an inaccessible_boot_device error. The legacy OS lacks the modern AWS Nitro NVMe and Elastic Network Adapter ENA drivers required to boot on newer EC2 hardware. I do not attempt to rebuild the application from scratch that destroys the timeline. Instead, I boot a temporary helper EC2 instance running a modern Windows server. I detach the corrupted 2008 EBS volume and attach it to the helper instance as a secondary drive. Using standard Windows command line tools DISM, I manually inject the AWS PV, NVMe, and ENA drivers directly into the legacy offline driver store and registry. I reattach the volume to the original instance and boot it successfully on an older instance type like M4 or T2 that natively supports legacy virtualization. The key insight is that OS obsolescence is not a migration blocker. If you understand raw block storage manipulation, you can perform open-heart surgery on an EBS volume without booting the OS. Pro tip: you do not actually have to do this manually. AWS Systems Manager has an automation runbook called AWS Support Upgrade Windows AWS Drivers. Execute this runbook against your offline EBS volume. It automatically mounts the drive, injects all required drivers, and repairs the boot sector in under 5 minutes.
Chapter 4. Conclusion.
You have survived the execution phase. By mastering split-brain recoveries, bypassing global DNS caching nightmares, and navigating 15-minute rollback windows, you've proven you can safely land mission-critical workloads in AWS under extreme pressure.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Chapter 4 to Chapter 5. Transition to Post-Migration.
The servers are running in AWS, and the cutover war room has been decommissioned. But a migration is not over just because the data moved. Now comes the hangover, skyrocketing bills, unoptimized latency, and messy security privileges. It's time to tune the engine.
Chapter 5. Post-Migration Optimization and Governance.
This chapter separates cloud mechanics from cloud architects. We will tackle the dreaded cloud shock invoice, debug massive latency penalties, retrofit zero-trust IAM policies, and architect multi-region disaster recovery on tight budgets.
Here are Chapter 5 scenarios we are going to cover.
Scenario 61, remediating cloud shock 300% bill increase. Scenario 62, diagnosing a 3 times application latency increase post-cutover. Scenario 63, retroactively implementing least privilege IAM. Scenario 64, architecting 1-hour RTO multi-region disaster recovery. Scenario 65, integrating AWS fault injection service for chaos engineering. Scenario 66, hitting the EC2 vertical scaling limit on a monolithic DB. Scenario 67, designing auto-scaling for upcoming holiday spikes. Scenario 68, resolving global latency with AWS Global Accelerator. Scenario 69, minimizing AWS egress fees in a hybrid environment. Scenario 70, configuring immutable audit trails for regulators. Scenario 71, conducting an AWS well-architected review post-migration. Scenario 72, managing change, stakeholders, and upskilling next. We face the angry CFO and fix the post-migration fallout.
Scenario 61, Cloud Shock. 30 days after a successful lift and shift, the CFO calls you panicking because the AWS monthly bill is 300% higher than their on-premises operational costs. How do you investigate and remediate this?
Answer: if you do not find the financial bleed instantly, leadership will halt all future migration waves and brand the cloud program a failure. I do not look at active compute first, I look for the waste. I immediately open AWS Cost Explorer and hunt for ghost resources, unattached EBS volumes, orphaned elastic IPs, and NAT gateways left running in abandoned migration test VPCs. Once the bleeding is stopped, I run AWS Compute Optimizer. Because this was a raw lift and shift, we brought over peak hardware sizing. I aggressively downsize EC2 instances based on P90 CPU metrics rather than theoretical maximums, and transition expensive GP2/IO1 volumes to cost-optimized GP3. Finally, I commit the verified baseline infrastructure to a 1-year compute savings plan to instantly slash on-demand rates by 30% plus. The key insight is that cloud shock isn't a failure of the cloud. It's the mathematical penalty for running elastic infrastructure with a static data center mindset. Pro tip: check the S3 billing reports for incomplete multi-part uploads. I've seen clients waste thousands of dollars a month on terabytes of invisible, failed migration data transfers because they didn't configure an S3 lifecycle rule to abort them after 7 days.
Scenario 62, a migrated application's response time increased by 3 times compared to its on-premises baseline. Customers are complaining. Walk me through your performance diagnostic steps.
Answer: every second of latency is causing cart abandonment and direct revenue loss. I do not throw more EC2 compute at the problem. A massive slowdown post-migration is almost always a network traversal or protocol issue. I use AWS X-Ray and VPC flow logs to trace a single request end-to-end. The data reveals that the legacy application is making 50 synchronous serial database queries per page load. On premises, with 0.1 milliseconds latency over a local switch, this bad code was invisible. Over a hybrid direct connect with 5 milliseconds latency, or across AWS availability zones, it compounds into a massive delay. I immediately implement Amazon Elasticache readies to absorb the read-heavy queries locally, and I push the app team to consolidate the N+1 SQL calls into a single stored procedure. The key insight is that a lift and shift perfectly preserves your legacy technical debt, but the cloud's network physics will instantly weaponize that debt against your users. Pro tip: Check if your migrated application is routing traffic through a NAT gateway just to talk to another internal AWS service like S3 or DynamoDB. Deploying VPC gateway endpoints bypasses the NAT entirely, instantly reducing latency and saving you massive data processing fees.
Scenario 63. Security flags that the environment has hundreds of overly permissive IAM roles created during the migration rush. How do you implement least privilege retroactively without breaking production?
Answer: this is a blast radius reduction exercise. You must surgically strip permissions based on empirical data without severing undocumented application dependencies. 1. Deploy IAM Access Analyzer to generate restrictive policies based on actual cloud trail activity. Guessing which permissions to remove manually guarantees a production outage when a monthly cron job finally runs. 2. Establish a definitive 30 to 90-day activity baseline via Amazon Athena and CloudTrail. Revoking access based on only 48 hours of telemetry will inevitably break quarterly financial reporting scripts that require broader access. 3. Attach the newly generated least privilege policy alongside the original administrator policy and use the IAM policy simulator to verify the application still functions perfectly within the new logical bounds. 4. Detach the overly permissive policies only during a controlled maintenance window with operations on standby. Failing to treat IAM rollbacks like application code deployments leads to extended, unrecoverable downtime. 5. Enforce permission boundaries on all developer and CI and CD roles. This allows teams to provision their own scoped IAM roles for new microservices, but physically prevents them from escalating those roles to administrator level. 6. Implement AWS config rules to actively alert and auto-remediate the creation of any new policy containing the action :* wildcard. Retroactively fixing permissions is useless if your deployment pipeline keeps generating open policies. 7. If you blindly revoke administrator access to satisfy an audit without analyzing the full usage window, you will sever the backup agent's S3 write permissions, causing silent data loss that you will not discover until a disaster occurs. Pro tip: use AWS IAM Identity Center to push read-only and operator permission sets globally. If a developer needs emergency write access to fix a production issue, use a temporary, time-bound session via AWS Systems Manager instead of permanently granting them IAM write permissions.
Scenario 64. The client now wants a multi-region disaster recovery setup for their newly migrated workloads. They require an RTO of 1 hour and RPO of near zero. How do you architect this?
Answer: achieving a 1-hour RTO and near zero RPO requires a highly automated pilot-light architecture that balances extreme data availability against infrastructure costs. 1. Deploy Amazon Aurora Global Database to replicate the data tier across regions with typical latency under 1 second. Relying on scheduled cross-region EBS snapshots will miss the near zero RPO requirement entirely. 2. Configure AWS Elastic Disaster Recovery (DRS) for the application tier. DRS continuously replicates block-level EC2 state to a low-cost staging area in the secondary region, dramatically reducing your compute bill during peacetime. 3. Implement Amazon Route 53 Application Recovery Controller to manage the complex, multi-step DNS failover routing. Relying on manual DNS updates during a regional outage guarantees you will miss your strict 1-hour RTO. 4. Define infrastructure as code IAC using Terraform to automatically spin up the full production compute fleet in the DR region only when a failover is initiated, maintaining a true cost-effective pilot-light state. 5. Replicate critical S3 buckets using cross-region replication CRR with replication time control RTC enabled. Without RTC, AWS provides no SLA on replication time, meaning a sudden outage could result in lost object data. 6. Execute a mandatory game day failover drill every quarter. An untested DR plan is merely a hypothesis, and failing to simulate a regional outage guarantees your runbooks will collapse during a real crisis. 7. If your secondary region has low default service quotas, for example, vCPU limits. Your automated failover will crash when trying to spin up 100 EC2 instances, leaving you stranded despite having perfect data replication. Pro tip: do not use the same KMS customer managed key CMK alias across both regions without replicating the actual key material using AWS KMS multi-region keys. If the DR region cannot decrypt the replicated EBS volumes, your entire failover strategy is useless.
Scenario 65. Following a successful migration to Amazon EKS, the client wants to implement automated chaos engineering. How do you integrate AWS Fault Injection Service FIS?
Answer: chaos engineering is not about breaking things randomly. It is about validating Kubernetes self-healing mechanisms through controlled, measurable fault injection. 1. Configure FIS to target specific EKS pods and EC2 worker nodes using precise tag filters. Running FIS blindly without strict blast radius controls will inadvertently take down unrelated production namespaces. 2. Inject stress, fault CPU/memory exhaustion onto the worker nodes to validate that the Kubernetes horizontal pod autoscaler HPA correctly provisions new pods before the application performance degrades. 3. Simulate network black holes between specific microservices within the EKS mesh. If you do not test network partitions, you cannot verify that your circuit breakers and Istio retry logic actually prevent cascading failures. 4. Integrate FIS directly into your CI and CD pipeline, triggering a chaos experiment automatically in a staging environment before every major release prevents regressions in application resilience. 5. Establish strict CloudWatch stop conditions for every FIS experiment. If the injected fault causes the application 500 level error rate to breach a 1% threshold, FIS must automatically abort the test to protect the business. 6. Terminate random EC2 instances within the EKS managed node group to validate cluster autoscaler behavior. Failing to test node loss guarantees a capacity outage when AWS performs routine underlying hardware maintenance. 7. If your EKS workloads lack proper pod disruption budgets, a chaos test simulating node failure will evict all replicas of a critical microservice simultaneously, resulting in a hard outage rather than graceful degradation. Pro tip: before running FIS, ensure your EKS pods have properly configured readiness and liveness probes. Without these, Kubernetes will not know the pods are suffering under the injected faults, and it will continue routing live user traffic to dying containers.
Scenario 66. A monolithic database migrated via lift and shift has hit the performance limits of the largest available Amazon EC2 instance type. The client has no budget to refactor. How do you architect a solution?
Answer: the database is running on an X2 IEDN.32X large with 4 terabytes of RAM. The CPU is pegging at 98%, and you have officially hit the vertical scaling wall of the AWS cloud. If traffic increases by even 5% tomorrow, the database will lock up and take the business offline. Since I cannot rewrite the application to adopt microservices, I must offload the pressure at the infrastructure layer. I immediately deploy Amazon Elasticache for Redis as a query caching layer to absorb the massive volume of repetitive select queries. Next, I migrate the database engine to Amazon Aurora and deploy up to 15 Aurora read replicas, utilizing Aurora's custom endpoints to transparently route reporting and read only traffic away from the primary writer node. Finally, I implement Amazon RDS proxy to manage connection pooling, preventing thousands of application connections from exhausting the database's finite memory. The key insight is that when you hit the physical limits of vertical scaling, you do not necessarily need a massive code refactor. You need an intelligent proxy and caching architecture to decouple the read operations from the write bottleneck. Pro tip: use AWS Database Migration Service (DMS) to continuously replicate the heaviest, most unoptimized reporting tables to an Amazon Redshift cluster. Reroute the business intelligence dashboards to Redshift, instantly freeing up 30% of your primary database's transactional capacity.
The universal interview tip: Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Scenario 67. An e-commerce platform that used to crash on premises during festivals is now on AWS. How do you design an auto-scaling strategy for the upcoming holiday spike?
Answer: holiday traffic spikes are not gradual. They are instantaneous. You must shift from reactive capacity management to predictive and decoupled scaling. 1. Deploy AWS predictive scaling using historical traffic data from previous on-prem holidays. Waiting for reactive scaling during a 10,000 TPS burst guarantees 503 errors during the critical first 5 minutes. 2. Implement target tracking policies based on ALB request count per target. Scaling on CPU alone lags behind sudden connection spikes, causing dropped connections before new EC2 instances can spin up. 3. Pre-warm the application load balancer via an AWS support ticket 48 hours before the event. ALB nodes scale automatically but not instantly, and hitting a cold ALB with Black Friday traffic will throttle legitimate users. 4. Decouple database writes using Amazon SQS for order processing. If you scale EC2 instances by 500% without buffering the backend, you will instantly exhaust RDS connection limits and crash the database. 5. Configure step scaling policies for scale-in to be extremely conservative. Aggressive scale-in during minor traffic dips leads to instance thrashing and delayed responses on the next micro spike. 6. If you ignore subnet sizing in your VPC design, the auto-scaling group will exhaust available IP addresses mid-spike, physically preventing new nodes from launching during your highest revenue hour. Pro tip: pre-bake your AMIs with all application dependencies and use larger EC2 instance sizes during the spike. Bootstrapping user data scripts at boot time takes 3 to 5 minutes an eternity during a holiday rush, whereas pre-baked AMIs boot in seconds.
Scenario 68. A global application running in US East 1 has strict latency requirements for users in Europe and Asia. How do you redesign the network?
Answer: you cannot change the speed of light, but you can change how traffic traverses the internet by onboarding users to the AWS backbone as early as possible. 1. Deploy AWS Global Accelerator to route Europe and Asia users onto the AWS private global backbone at the closest edge location. Relying on standard BGP over the public internet introduces variable jitter and high packet loss. 2. Terminate TCP and TLS connections at the global accelerator edge. Performing the multi-round-trip TLS handshake across the Atlantic Ocean cripples time to first byte TTFB for European customers. 3. Implement Amazon CloudFront for static assets with caching headers tuned to 24 plus hours. Fetching images from US East 1 for every Asian user wastes bandwidth and adds 200 milliseconds of latency to every page load. 4. Transition backend APIs from ALB domains to global accelerator endpoints. ALB IP addresses change dynamically, forcing global clients to constantly re-resolve DNS, whereas GA provides two static unicast IPs. 5. Optimize database read latency by deploying Amazon Aurora Global Database read replicas in EU Central 1 and AP Northeast 1, forcing global users to read data across an ocean guarantees a sluggish application experience. 6. If your application hardcodes the regional ALB domain name instead of the global accelerator endpoint, the traffic bypasses the edge network entirely, rendering your expensive latency optimization useless. Pro tip: use CloudFront's Origin Shield in US East 1. If multiple edge caches in Asia and Europe expire simultaneously, Origin Shield acts as a centralized caching layer, preventing a sudden thundering herd of requests from crashing your backend servers.
Scenario 69, the migration is done, but the client still operates a hybrid environment. How do you design a highly cost-effective data transfer strategy to minimize AWS egress fees?
Answer: the CFO hands you an AWS bill with a massive $50,000 line item strictly for data transfer out and threatens to pull workloads back on premises. If this financial bleed continues, the entire migration business case flips negative within a single quarter. I do not attempt to negotiate AWS pricing. I immediately run AWS Cost Explorer and VPC flow logs to trace the egress. The data reveals that the on-premises analytics cluster is pulling terabytes of data from S3 over the public internet, traversing our expensive NAT gateways in the process. I instantly deploy VPC gateway endpoints for S3 to keep all internal cloud traffic on the free AWS backbone, bypassing the NAT completely. Next, I route the hybrid data pulls over our existing AWS Direct Connect private VIF, which charges significantly lower egress rates than internet transfer. The key insight is that in a hybrid cloud, architecture is not just about connectivity. It is about tariff management, because the cloud penalizes bad routing with hard dollars. Pro tip: check your cross-a-Z traffic. If your web servers in a Z are constantly querying a database node in a ZB because you didn't configure a Z affinity on your load balancer, AWS charges you $0.01 per GB in both directions. Fixing this one routing flaw can instantly slash your internal network bill by 50%.
Scenario 70, regulatory auditors require detailed logging, reporting, and immutable trails for all actions taken in the new AWS environment. Which specific services do you enable and configure?
Answer: compliance requires cryptographic proof that data hasn't been altered. You must build an automated tamper-proof surveillance perimeter across the organization. 1. Enable AWS CloudTrail natively across all regions and accounts using an organization trail. Allowing individual accounts to manage their own trails introduces gaps and allows malicious actors to turn off logging. 2. Direct all CloudTrail logs to a centralized, highly restricted S3 bucket protected by S3 object lock and compliance mode. Without worm protection, compromised administrators can permanently delete the audit evidence of their breach. 3. Deploy AWS config to record resource configuration changes continuously. If an auditor asks who opened a security group port 3 months ago, CloudTrail shows the API call, but config proves exactly what the rule looked like. 4. Encrypt the central audit S3 bucket using an AWS KMS customer-managed key CMK with strict key policies. Relying solely on default S3 encryption is insufficient for highly regulated environments demanding independent cryptographic control. 5. Implement service control policies (SCPs) to deny the CloudTrail stop logging action across the entire AWS organization. If a local administrator can disable the logging agent, your compliance certification is instantly invalidated. 6. If you fail to configure CloudTrail log file validation, auditors will reject your logs as inadmissible evidence, because you cannot cryptographically prove the files were not tampered with post-delivery. Pro tip: use Amazon Athena to query your CloudTrail S3 bucket directly. When an auditor asks for a list of all failed console logins over the last 90 days, you can run a single SQL query and hand them a CSV in 5 minutes, rather than spending weeks parsing raw JSON files.
Scenario 71. You are asked to conduct an AWS well-architected framework review on a workload that was migrated by a different vendor 6 months ago. Which pillars do you focus on first?
Answer: inheriting a vendor's migration means inheriting their technical debt. You must prioritize existential threats over architectural elegance. 1. Prioritize the security and cost optimization pillars immediately over reliability or performance. Inherited environments are notorious for open S3 buckets and massive over-provisioning that expose the business to immediate risk. 2. Deploy AWS IAM Access Analyzer to hunt for cross-account trust relationships and public exposure. A legacy vendor often leaves behind backdoor IAM roles for their own support access that must be severed on day 1. 3. Utilize AWS Compute Optimizer to identify EC2 instances running at less than 10% utilization for the last 6 months. A vendor executing a blind lift and shift preserves legacy data center waste that you must clean up to prove ROI. 4. Audit the VPC architecture for single AZ dependencies using AWS Trusted Advisor. If the previous vendor deployed critical NAT gateways or RDS instances in only one availability zone, the next localized AWS hardware failure will take down the company. 5. Review the backup retention policies in AWS Backup. Vendors often configure daily snapshots but fail to configure lifecycle transitions, leaving 6 months of expensive snapshots sitting in standard storage tiers. 6. If you accept accountability for the environment without baselining the architecture, the next security breach or billing spike becomes your fault, destroying your credibility with the client. Pro tip: look for hard-coded IAM access keys. Run an immediate credential report in IAM and disable any access key older than 90 days. Vendors notoriously embed long-lived, powerful access keys in application config files instead of using EC2 instance roles, creating a ticking time bomb for a breach.
Scenario 72. How do you manage the human element, specifically change management, and team upskilling, in the months immediately following a major cloud transition?
Answer: you've successfully cut over to AWS. But 3 weeks later you discover the operations team is still SSing directly into production EC2 instances to manually tweak configuration files, completely bypassing source control. If you allow this click ops culture to persist, your immutable cloud environment will rapidly degrade into an undocumented, unscalable mess of configuration drift. I don't reprimand the team or lock them out of the console entirely, which only breeds resentment and shadow IT. Instead, I immediately block port 22 at the security group level and mandate the use of a AWS Systems Manager SSM Session Manager, enforcing that all terminal actions are logged to CloudTrail. I then pair the legacy sysadmins with cloud engineers to convert their most frequent manual tasks into automated SSM documents or Terraform scripts. The key insight is that post-migration resistance is rarely malice. It is the fear of obsolescence. You secure the cloud not by taking away their access, but by aggressively upskilling them to operate at a higher level of abstraction. Pro tip: create a cloud center of excellence CCOE and gamify the transition. Give the legacy ops team read-only access to AWS Cost Explorer and challenge them to find waste. When a former hardware admin uses their deep system knowledge to right-size an EC2 instance and saves $5,000 a month, they instantly transform from a cloud skeptic into your biggest cloud advocate.
Chapter 5. Conclusion.
You have successfully stabilized the post-migration environment. By diagnosing network latency, ruthlessly cutting cloud shock waste, and retrofitting zero-trust IAM policies, you have transformed a messy lift and shift into a highly optimized, enterprise-grade cloud estate.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the Masterclass.
Chapter 5 to Chapter 6, Transition to Modernization.
Running legacy servers on someone else's hypervisor is only the beginning. The true value of cloud engineering lies in what comes next. We must now look to the cutting edge: serverless refactoring, specialized silicon, carbon optimization, and generative AI.
Chapter 6, Modernization and 2026 plus Edge Scenarios.
This is the domain of the elite cloud architect. We will dismantle monoliths using the Strangler Fig pattern, escape commercial databases, harness AWS Graviton, and migrate legacy mainframes. This chapter prepares you for the highest-paying challenges in the industry. Scenario 73, the Strangler Fig pattern for massive monoliths. Scenario 74, migrating legacy GPU/AI to AWS Bedrock and Trainium. Scenario 75, GenAI-assisted .NET refactoring with Amazon Q. Scenario 76, executing cross-architecture migrations to AWS Graviton. Scenario 77, architecting for net zero sustainability mandates. Scenario 78, migrating legacy IBM mainframes to AWS. Scenario 79, refactoring to EKS under a strict 3-month deadline. Scenario 80, escaping commercial DB licensing Oracle to Aurora OSS. Scenario 81, multi-cloud migrations Azure/GCP directly to AWS. Scenario 82, modernizing distributed cron jobs to Event Bridge. Scenario 83, migrating heavy ETL batch jobs to AWS Glue/EMR. Scenario 84, modernizing Hadoop into an Amazon S3 data lake. Scenario 85, preserving NTFS permissions on AWS FSx migrations. Scenario 86, architecting legacy multicast networking in the cloud. Scenario 87, seamless SFTP migrations using AWS Transfer Family. Scenario 88, Gov Cloud and top-secret compliance architectures. Scenario 89, emulating bare metal shared memory in AWS. Scenario 90, migrating clients with zero DevOps maturity. Scenario 91, fixing synchronous multi-AZ database latency limits. Scenario 92, modernizing RabbitMQ to serverless messaging. Next, we break apart the monolith and enter the 2026 plus architecture era.
Scenario 73, a company wants to migrate and convert a massive on-premises monolith into AWS microservices. Walk me through how you plan and execute the Strangler Fig pattern without downtime.
Answer: you cannot execute a big bang rewrite of a monolith without destroying the business. You must implement an edge proxy to slowly siphon traffic to new microservices. 1. Deploy Amazon API Gateway or an application load balancer in front of the on-premises monolith to act as the central routing proxy. Without an abstraction layer at the network edge, You cannot dynamically shift traffic without relying on highly volatile DNS updates. 2. Peel off the lowest risk. Stateless read-only endpoints like product catalogs and rewrite them as AWS Lambda or Amazon EKS microservices. Attempting to decouple highly stateful transactional modules first guarantees data inconsistency and immediate rollback. 3. Maintain the legacy on-premises database as the temporary single source of truth, connecting the new cloud microservices back via AWS Direct Connect. Splitting the database schema before the application logic is fully decoupled will cause catastrophic foreign key and join failures. 4. Implement AWS Database Migration Service DMS with continuous replication CDC to synchronize the legacy monolith database to the new microservice databases. If you do not sync the state, the legacy app and the new microservices will operate in split-brain isolation. 5. Use weighted routing rules at the ALB to send 1% of traffic to the new microservice. Monitoring CloudWatch for 500-level errors and elevated latency, blindly shifting 100% of traffic to a newly refactored service bypasses the entire safety mechanism of the strangler pattern. 6. If you fail to implement distributed tracing using AWS X-Ray, debugging an API failure that traverses both the new cloud microservices and the legacy monolith becomes a complete operational impossibility. Pro tip: do not rewrite the legacy code during the initial microservice extraction. Copy the exact business logic over to the cloud function first. Refactoring infrastructure and application logic simultaneously removes your baseline, making it impossible to know if a bug was caused by the cloud environment or the new code.
Scenario 74. You are tasked with migrating an on-premises generative AI workload utilizing legacy GPU clusters. How do you transition their models to utilize Amazon Bedrock and AWS Silicon?
Answer: lifting and shifting AI clusters is a financial trap. You must decouple the models from the raw compute layer to survive in the cloud. 1. Transition foundational model inference directly to Amazon Bedrock. Managing raw EC2 GPU instances for standard inference locks you into severe capacity constraints and astronomical hourly costs that destroy the cloud business case. 2. Recompile custom, proprietary training models to utilize AWS Trainium and Inferentia chips via the AWS Neuron SDK, blindly demanding NVIDIA H100 or A100 instances in AWS will result in months of waiting for capacity allocation while burning your budget. 3. Migrate legacy on-premises vector data directly to Amazon OpenSearch serverless with the vector engine enabled. Maintaining self-hosted vector databases on EC2 forces you to manually manage index scaling and shard rebalancing during RAG retrieval augmented generation spikes. 4. If you fail to implement Amazon Macy and strict IAM boundaries on the S3 buckets feeding your training pipelines, you risk accidentally injecting highly classified corporate data into a foundational model, creating an irreversible compliance breach.
Scenario 75. Your client wants to leverage Amazon Q and GenAI tools to massively accelerate the refactoring of thousands of lines of legacy .NET framework code to modern .NET Linux compatible. How do you design this pipeline?
Answer: the CIO refuses to pay for another 3-year Windows Server Enterprise renewal, demanding the entire C# codebase run on Linux containers in 90 days. I do not assign 50 developers to manually rewrite the code that guarantees syntax errors, regression bugs, and a missed deadline. I deploy AWS Microservice Extractor for .NET integrated with Amazon Q Developer to programmatically scan the repository, identifying Windows-specific dependencies like IIS or registry calls. I use Amazon Q to auto-generate the .NET 8 Linux-compatible equivalent code blocks. Crucially, I feed this AI-generated code directly into a rigorous, automated CI and CD pipeline, using AWS Code Build to instantly run unit tests and static analysis. The key insight is that code generators are incredibly fast but confidently wrong. You must treat LLMs as raw compilers, relying entirely on your automated testing pipeline to catch hallucinations before they break the target architecture. Pro tip: use the AWS Porting Assistant for .NET to generate a full compatibility assessment report before invoking any GenAI. It identifies NuGet package incompatibilities that no LLM can magically fix, allowing you to prioritize the manual library upgrades before attempting the automated code refactoring.
Scenario 76. To optimize costs, a client mandates that all compatible Java workloads must be migrated from x86 architecture directly to AWS Graviton ARM-based instances. How do you execute this?
Answer: Java is theoretically platform independent, but an architecture shift requires strict pipeline validation and multi-arch build strategies. 1. Upgrade the application to the latest long-term support LTS version of Amazon Corretto. Running ancient JVMs on ARM architecture bypasses the native Graviton performance optimizations and causes severe garbage collection pauses. 2. Update the CI and CD pipelines in AWS code build to generate multi-architecture Docker images using Docker builds. If you hardcode your image builds to ARM64, your developers will not be able to run the containers locally on their x86 laptops. 3. Deploy mixed architecture auto-scaling groups containing both x86 and Graviton instances during the rollout phase. A Big Bang switch to ARM isolates the environment, whereas a mixed group allows you to bleed traffic safely and roll back seamlessly. 4. If you ignore the native C/C++ libraries wrapped inside the Java code JNI, the application will compile perfectly, but instantly throw a fatal architecture exception the moment it attempts to execute a native method on the Graviton instance.
Scenario 77. Your client has an aggressive corporate sustainability mandate for 2030 and wants a migration strategy that explicitly minimizes their carbon footprint. How do you architect this?
Answer: Sustainability is no longer a marketing exercise. It is a physical architecture constraint requiring exact service selection and regional placement. 1. Mandate the migration target exclusively to AWS regions powered by 100% renewable energy such as EU North 1 or US West 2. Moving workloads to fossil fuel-heavy regions permanently caps your ability to achieve a net zero architecture. 2. Transition idle and batch workloads from permanent EC2 instances to AWS Lambda and Fargate. Serverless architectures share underlying hardware tenancy, drastically reducing the physical carbon waste of spinning idle CPUs. 3. Enforce aggressive AWS Graviton adoption across all compute layers. ARM-based silicon uses up to 60% less energy for the same performance output as traditional x86 processors, instantly shrinking the carbon footprint. 4. If you fail to baseline the on-premises power consumption before the migration, the AWS Customer Carbon Footprint tool is useless. You cannot mathematically prove the carbon ROI to the board without an accurate historical benchmark.
Scenario 78. You are tasked with migrating a legacy IBM mainframe running critical COBOL applications to AWS. What is your strategic approach to emulation, replatforming, or refactoring?
Answer: The mainframe lease expires in 8 months. The original COBOL developers retired a decade ago, and the batch jobs are failing silently. Attempting a massive automated code translation to Java under this deadline is a guaranteed multi-year failure that will destroy the core ledger. I abandon the refactor dream and pivot to a replatforming strategy using the AWS Mainframe Modernization service. I deploy Micro Focus to recompile the COBOL code to run natively on Amazon EC2, strictly preserving the core business logic exactly as it was written in 1995. I swapped the rigid hierarchical database for Amazon RDS Postgres SQL, utilizing schema mapping tools to translate the legacy EBCDIC data formats. The key insight is that mainframe migrations fail because teams try to modernize the infrastructure and the application code at the exact same time. You must emulate the logic in the cloud first to escape the hardware, and only then start peeling off microservices. Pro tip: pay extreme attention to the EBCDIC to ASCII data conversion. Mainframe COBOL applications rely heavily on specific sort orders where numbers are sorted differently than letters. If you do not implement a custom collation sequence in your new RDS database, Your financial batch reports will generate completely different output files post-migration.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Scenario 79. A retail client wants to refactor their on-premises application into containerized microservices on Amazon EKS, but their data center lease expires in exactly 3 months. How do you balance modernization with the strict deadline?
Answer: the data center lease is up in 90 days, but the CTO just mandated a full microservices rewrite on Amazon EKS. A proper Kubernetes refactor takes 12 months, attempting to decouple the database, rewrite the application logic, and build a container deployment pipeline in 90 days guarantees unbootable code and a physical eviction. I immediately veto the full rewrite and pivot to tactical containerization. We use the AWS App2 container tool to wrap the monolithic application in a Docker image without modifying a single line of business logic. We deploy this massive macro container to a single EKS node group and offload the database to Amazon RDS. The key insight is that deadlines do not respect architectural purity. Containerizing a monolith buys you the physical time to evacuate the facility, allowing you to strangle the monolith safely from within the cloud. Pro tip: beware of local file system dependencies. Legacy monoliths notoriously write stateful session data or logs to local disk. You must wrap the new macro container with an Amazon EFS mount. Otherwise, that stateful data will vanish every time the EKS pod restarts or scales.
Scenario 80. A client wants to completely abandon their expensive commercial database licenses and move to open-source Engine's Oracle/SQL server to Aurora OSS. Walk me through the exact tooling.
Answer: escaping commercial licensing requires a mathematically precise translation of proprietary schema logic, not just a data copy. 1. Run the AWS Schema Conversion Tool (SCT) to isolate read objects like proprietary PL/SQL packages or advanced triggers. Rewriting these manually is the critical path that dictates the entire migration timeline. 2. Deploy Babelfish for Aurora PostgreSQL. If the application code cannot be immediately modified to swap SQL dialects, forcing the application teams to rewrite thousands of complex legacy queries will stall the cloud project for years. 3. Configure AWS DMS with aggressive pre-validation to accurately map legacy data types, for example, Oracle number to PostgreSQL numeric. Silent truncation during translation will corrupt the financial ledger. 4. Execute dual running performance tests using AWS DMS continuous replication, An unoptimized open-source engine will lock up under commercial-level concurrency if you haven't tuned the Aurora parameter groups. 5. Establish a reverse replication DMS task back to the commercial database during the first 48 hours of cutover. If the OSS engine crashes under unpredictable production load, you must be able to fail back without data loss. 6. If you assume standard native backups translate perfectly, you will discover during a disaster that your custom RMN backup scripts are useless against Aurora, leaving you with zero recoverable snapshots. Pro tip: use the SCT Workload Qualification Framework (WQF). It automatically categorizes databases from 1 easy to 5 impossible without major rewrite. Present this to the CFO to pick off the low-hanging fruit and demonstrate immediate licensing ROI before tackling the complex core systems.
Scenario 81. An organization is moving workloads from Microsoft Azure and Google Cloud directly to AWS. What unique challenges and routing differences arise in a multi-cloud migration?
Answer: moving cloud to cloud introduces massive egress penalties and IAM translation traps that simply do not exist in traditional on-prem migrations. 1. Architect an immediate dedicated interconnect, for example, Megaport or Equinix, between the source cloud and AWS. Routing terabytes of block replication data over the public internet will trigger catastrophic egress fees from Azure or GCP. 2. Translate source IAM roles to AWS IAM using federated identities, assuming a one-to-one mapping between Azure RBAC and AWS IAM policies will inadvertently grant excessive cross-account permissions and violate zero trust. 3. Utilize AWS Application Migration Service (MGN) by treating the Azure/GCP VMs as on-premises physical servers. Attempting to export and convert native VMDK/VHD images manually introduces severe hypervisor driver panics on EC2. 4. Audit the source architecture for cloud-native managed services, for example, Azure SQL, GCP BigQuery. You cannot install a block-level replication agent on a PaaS database, forcing a pivot to logical replication via AWS DMS. 5. Refactor hard-coded cloud-specific SDKs in the application code. An Azure Blob Storage API call will critically crash the application when it attempts to run inside an AWS EC2 instance. 6. If you fail to strip cloud-native DNS configurations via MGN post-launch scripts, the EC2 instances will constantly try to route traffic back to the dead Azure VPC, causing intermittent application timeouts. Pro tip: beware of overlapping metadata IP addresses. Both Azure and AWS use 169.254.169.254 for instance metadata. Ensure any startup scripts expecting Azure instance metadata are completely disabled before the cutover, or the EC2 instances will hang on boot.
Scenario 82. An enterprise has thousands of complex scheduled cron jobs spread across individual legacy servers. How do you centralize and modernize this scheduling architecture into Amazon Event Bridge?
Answer: you've successfully migrated a massive fleet of Linux servers, but the application intermittently fails because 500 decoupled. Undocumented cron jobs are misfiring across instances in unpredictable sequences. Leaving cron schedules tied to individual EC2 instances breaks the elasticity of auto-scaling, because terminating a node permanently deletes the scheduled task. I immediately extract the cron schedules from the OS level and centralize them into Amazon Event Bridge. I decouple the execution environment by pointing the Event Bridge rules to trigger AWS Systems Manager SSM run command directly on the target fleet based on resource tags. The key insight is that modernization is not just about compute. It is about state abstraction. Extracting scheduling logic from the operating system is what transforms a fragile server into an ephemeral, scalable cloud asset. Pro tip: use Event Bridge's dead letter queues DLQ tied to an SQSQ. Standard cron jobs fail silently in syslog. Event Bridge DLQs ensure that if a target EC2 instance is down or an API fails, the misscheduled event is captured, alerted, and ready for replay.
Scenario 83. A company has heavy, nightly on-premises ETL batch processing jobs. How do you modernize this workflow by migrating it to AWS Glue or Amazon EMR?
Answer: migrating heavy ETL pipelines requires decoupling the storage layer from the compute clusters to prevent massive over-provisioning and wasted spend. 1. Transition rigid, on-premises ETL scripts Informatica, or Talent to PySpark jobs running on AWS Glue, retaining legacy ETL orchestration on permanent EC2 instances, forces you to pay 24/7 compute rates for jobs that only run for 3 hours a night. 2. Separate the data lake storage into Amazon S3 before launching Amazon EMR. Relying on HDFS Hadoop distributed file system on EC2 instances permanently binds your compute scale to your storage footprint, obliterating cloud elasticity. 3. Implement AWS step functions to orchestrate the dependency graph of the batch jobs. Relying on legacy time-based scheduling instead of event-driven triggers guarantees pipeline failures when upstream data extracts are unexpectedly delayed. 4. Configure EMR managed scaling or Glue auto scaling to dynamically provision worker nodes based on yarn memory demands. Failing to tune cluster scaling will result in out-of-memory crashes during month-end data spikes. 5. Secure the pipeline by injecting database connection strings dynamically using AWS Secrets Manager. Hard-coding credentials in modernized PySpark jobs will inadvertently expose plaintext passwords in the CloudWatch logs. 6. If you fail to monitor S3 API limits during highly parallelized Glue jobs, your ETL pipeline will trigger slowdown 503 errors from S3, severely bottlenecking the nightly ingestion process. Pro tip: use AWS Glue crawlers to automatically infer the schema of your incoming flat files. This eliminates the need to manually code rigid DDL statements, allowing your ETL pipeline to dynamically adapt when upstream vendors silently change their CSV column headers.
Scenario 84. How do you migrate massive, siloed on-premises Hadoop clusters into a modernized AWS data lake utilizing Amazon S3, AWS Lake Formation, and Amazon Athena?
Answer: Hadoop migrations require a fundamental paradigm shift from compute-attached storage to a decoupled, serverless querying architecture. 1. Execute the massive data transfer from HDFS to Amazon S3 using AWS Snowball Edge. Attempting to query legacy HDFS directly over a hybrid link will time out your analytics tools and completely saturate the direct connect. 2. Convert bloated CSV and JSON files into columnar formats like Parquet or ORC during the ingest phase using AWS Glue. Querying petabytes of raw CSV data in S3 will result in agonizingly slow performance and exorbitant Athena scan costs. 3. Deploy AWS Lake Formation to establish column-level and row-level security policies. Relying on basic S3 bucket policies for a massive data lake strips the granular access control required by InfoSec to protect PII. 4. Transition end-user BI reporting directly to Amazon Athena for serverless querying, provisioning permanent EMR clusters just to support ad hoc SQL queries, replicates the exact cost inefficiencies of your legacy Hadoop environment. 5. Implement Amazon S3 object expiration rules specifically for the Athena query results bucket. Athena automatically saves every query result as a new CSV, which can silently consume terabytes of storage if not aggressively purged. 6. If you fail to partition the S3 data logically, for example, by year or month or day, every Athena query will execute a full bucket scan, mathematically guaranteeing a six-figure AWS billing shock at the end of the month. Pro tip: turn on S3 requester pays for cross-account analytics. If a different business unit runs a poorly optimized Athena query against your data lake bucket, they absorb the API and data transfer costs, protecting your department's infrastructure budget.
Scenario 85. You are migrating a large fleet of Windows file servers to AWS. How do you preserve all NTFS permissions and Active Directory ACLs while implementing highly available storage?
Answer: the security team has mandated that decades of complex NTFS permissions and nested Active Directory ACLs must be preserved with 100% fidelity. Simply copying these files to S3 or EFS strips the proprietary Windows security descriptors. If a standard copy tool is used, the CEO's highly restricted HR folders will instantly become globally readable to the entire company upon cutover. I mandate the use of Amazon FSx for Windows File Server and deploy AWS Data Sync using a dedicated SMB location configuration. I configure the data sync task to explicitly copy all ownership, SACLs, and DACLs alongside the data. To ensure the security identifier's SIDs resolve correctly, I join the FSx file system directly to the legacy AWS managed Microsoft AD. The key insight is that in file server migrations, the data movement is trivial. Identity preservation is the entire battle. Pro tip: before the final sync, use a script to scan the on-premises file shares for path lengths exceeding the Windows 260-character limit max_path. Deeply nested legacy folders will cause data sync tasks to fail silently on individual files, leaving critical user data permanently stranded on premises.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Scenario 86. A workload heavily relies on multicast networking, which is historically difficult in the cloud. How do you architect the migration of this workload to AWS?
Answer: standard AWS VPCs strictly block broadcast and multicast traffic. You must fundamentally alter the network routing plane to support legacy multicast applications. 1. Deploy AWS Transit Gateway (TGW) and explicitly enable multicast domain support during creation. Attempting to run legacy multicast software on a standard VPC will result in silently dropped packets at the hypervisor level. 2. Register the target VPC subnets to the TGW multicast domain and associate the EC2 Elastic Network Interfaces ENIs with the specific multicast group IP addresses. 3. Enable Internet Group Management Protocol (IGMP v2) support on the Transit Gateway to allow EC2 instances to dynamically join and leave multicast groups without requiring manual AWS console intervention. 4. If you assume AWS Transit Gateway Multicast operates across multiple AWS regions natively, your global deployment will fail. TGW Multicast is strictly bound to a single region and cannot be peered. 5. Reconfigure the legacy application to use unicast fallback mechanisms if absolute packet delivery guarantees are required. Cloud Multicast operates on a best effort UDP basis and does not natively guarantee packet ordering. 6. If you fail to adjust the time to live TTL threshold on the legacy application's multicast packets to account for the transit gateway hops, the traffic will be dropped before reaching the subscriber instances. Pro tip: AWS Transit Gateway does not natively route multicast traffic down a standard direct connect connection. To span multicast from AWS back to your on-premises data center, you must encapsulate the multicast traffic inside a GRE generic routing encapsulation tunnel, terminating on a dedicated transit gateway connect attachment.
Scenario 87. A business relies on SFTP for external vendor data drops using outdated on-prem Linux servers. How do you seamlessly migrate thousands of SFTP users to AWS Transfer Family without them having to change their credentials?
Answer: coordinating SSH key and password updates with 1,000 stubborn external B2B vendors is a logistical impossibility that will stall the migration for a year. I completely decouple the server infrastructure from the identity layer by deploying AWS Transfer Family backed by Amazon S3. Instead of relying on local Linux shadow files, I integrate the Transfer Family endpoint with a custom AWS Lambda identity provider. This Lambda function queries the legacy hashed passwords and SSH keys stored securely in AWS Secrets Manager or an existing Active Directory via LDAP. The external vendors point to the new Elastic IP, use their exact legacy credentials, and the migration remains 100% transparent to them. The key insight is that B2B migrations succeed only when you eliminate friction for the external partner. Forcing your tech debt resolution onto your clients will severely damage business relationships. Pro tip: to make the cutover truly invisible, use AWS Elastic IP EIP. Bring your own IPBYOIP. By migrating your legacy on-premises public IP subnet to AWS, you assign the exact old IP address to the AWS Transfer Family endpoint, neutralizing the need for 1,000 vendors to update their corporate firewall whitelists.
Scenario 88. You are migrating highly classified, restricted workloads. Walk me through the compliance and architectural differences of migrating to an AWS Gov Cloud or top secret region.
Answer: migrating to a classified or ITAR-compliant region requires abandoning commercial cloud assumptions. The architecture must survive within a physically and logically isolated partition. 1. Mandate the use of FIPS 140-2 validated API endpoints for all AWS service interactions. Hitting standard commercial AWS endpoints from within a Gov Cloud environment will result in immediate compliance audit failure. 2. Audit the AWS Gov Cloud Service Availability Matrix before signing off on the target architecture, assuming cutting-edge managed services like Amazon Bedrock or advanced AI services are available in Gov Cloud guarantees mid-project architectural roadblocks. 3. Establish strict cross-partition identity architectures using SAML federation. You cannot directly peer IAM roles between the standard AWS partition and the AWS US Gov partition, forcing you to decouple identity entirely. 4. If you accidentally log ITAR restricted resource names or metadata into a standard commercial cloud trail or billing bucket, you trigger a massive federal spillage incident requiring immediate government notification. 5. Implement AWS KMS using hardware security modules Cloud HSM if your specific federal contract requires single-tenant cryptographic key isolation. 6. If you design your infrastructure as code scripts using hard-coded standard commercial ARNs, every single deployment will crash in Gov Cloud because the namespace completely changes. Pro tip: hard-coding ARN:AWS in your Terraform or CloudFormation templates is a fatal error when migrating to restricted regions. Always use the data.aus_partition construct to dynamically inject ARN:AWS US Gov or ARN:AWS ISO, ensuring your code remains portable across commercial and classified domains.
Scenario 89. A legacy application relies heavily on extremely fast shared memory between processes running on the same bare metal server. How do you architect this requirement in AWS?
Answer: the high-frequency trading application just failed its cloud load test because the standard EC2 hypervisor overhead broke its reliance on nanosecond inter-process communication, IPC, via shared physical RAM. You cannot refactor this into decoupled network microservices without introducing millisecond latency, which destroys the application's core value. I abandon standard virtualized compute and migrate the workload to Amazon EC2 bare metal instances, for example, M5.metal. This removes the AWS Nitro hypervisor entirely, granting the application direct hardware access to CPU sockets and NUMA non-uniform memory access nodes, allowing local shared memory mappings POSIX SHM to function exactly as they did on premises. The key insight is that software physics sometimes overrides cloud elasticity. When memory access speed is the product, virtualization is the enemy. Pro tip: when using bare metal instances for high-performance shared memory, ensure your OS is configured for huge pages. By increasing the memory page size from the default 4 kilobytes to 1 gigabytes, you drastically reduce translation look-aside buffer TLB misses, clawing back critical microseconds of performance.
Scenario 90. A client wants cloud first, but has absolutely zero DevOps maturity, no CI and CD, no infrastructure as code IAC, everything is manual. How do you structure the migration?
Answer: the CIO has mandated a cloud-native migration by Q4, but the infrastructure team has never written a line of Terraform and manages production via remote desktop. If you force an advanced Kubernetes and CI and CD refactor on day one, the team will mutiny and the migration will stall indefinitely. I decouple the infrastructure automation from the application migration. I personally bootstrap a foundational landing zone using AWS Control Tower and force the use of Terraform for all base network and IAM provisioning, physically locking the console to prevent click ops. For the applications, we perform an automated lift and shift using AWS MGN. Once the servers are stable in AWS, I pair the legacy sysadmins with my cloud engineers to reverse engineer the migrated EC2 configurations into AWS Cloud Formation or Terraform code. The key insight is that you cannot buy DevOps maturity. You must drag the organization into it by migrating the workloads first and using the new cloud environment as the mandatory training ground. Pro tip: use the AWS Systems Manager (SSM Fleet Manager) to ease the transition for Windows admins. It provides a GUI-based remote management console directly in the browser, allowing them to manage their servers without needing open RDP ports, while slowly introducing them to the AWS console ecosystem.
Scenario 91. During a migration, you realize that synchronous database replication across 2 AWS availability zones is causing too much latency for the legacy application to handle. How do you adjust the architecture?
Answer: the database cutover succeeds, but the legacy application instantly gridlocks. The required synchronous write across 2 AWS availability zones adds 2 milliseconds of latency to every single commit. Because the legacy code opens a database transaction, makes an external API call, and then closes the transaction, that 2 milliseconds penalty compounds until the connection pool is entirely exhausted. Lowering the instance size will not fix the speed of light. I immediately disable multi-AZ synchronous replication on the RDS instance, pivoting the database to a single AZ deployment to eliminate the cross-zone write penalty. To compensate for the lost high availability, I deploy a cross-AZ read replica using asynchronous replication. In the event of a zone failure, we accept a 1-minute RTO to manually promote the async replica. The key insight is that legacy code dictates cloud topology. You must actively trade strict high availability for application survival until the code can be refactored. Pro tip: if abandoning multi-AZ is unacceptable to the business, you must move from RDS to Amazon Aurora. Aurora's storage engine decouples compute from storage, writing directly to a highly optimized quorum-based storage fleet, effectively eliminating the massive performance penalty of traditional block-level synchronous replication.
Scenario 92. A client wants to modernize their message queuing system from on-premises RabbitMQ to AWS fully managed serverless services. Walk me through the decision-making process.
Answer: Replacing a legacy message broker requires dissecting the application's exact routing, ordering, and fan-out requirements before selecting the AWS equivalent. 1. Replace rigid point-to-point RabbitMQ queues with Amazon SQS standard queues for massive horizontal scaling and resilience. Attempting to manage EC2-based brokers wastes engineering time on patching instead of feature development. 2. Implement Amazon SQS FIFO first-in first-out queues if the legacy application strictly requires message ordering. Replacing an ordered RabbitMQ queue with standard SQS guarantees out-of-sequence processing that will silently corrupt downstream databases. 3. Transition RabbitMQ topic exchanges to Amazon SNS. SNS provides the pub-sub fan-out capability required to push a single event to multiple independent SQS queues or Lambda functions concurrently. 4. Deploy Amazon Event Bridge if the legacy routing logic relies on deep inspection of the message payload. Standard SNS can only filter by attributes, whereas Event Bridge can dynamically route traffic based on complex JSON payload structures. 5. If you fail to adjust the application's consumer polling logic for SQS, you will trigger thousands of empty API calls per minute, resulting in an unnecessarily bloated AWS bill. 6. If the legacy application uses advanced AMQP features like message routing keys that are too tightly coupled to refactor, you must abandon serverless and pivot to Amazon MQ for RabbitMQ to ensure compatibility. Pro tip: always configure a dead letter QDLQ with Amazon SQS during the modernization phase. If a poison message format from the legacy application hits the new cloud consumer, the DLQ catches the failure automatically, preventing an infinite processing loop that destroys your serverless budget.
Chapter 6 Conclusion.
You have conquered the final frontier of cloud migrations. By implementing the Strangler Fig pattern, surviving bare metal latency constraints, and modernizing legacy code with generative AI, you have evolved from a migration technician into a true cloud architect. You do not just move workloads, you transform them.
The ultimate masterclass conclusion.
From undocumented 1,500 server messes and massive data center evacuations to multi-region disaster recovery and GenAI refactoring, this is the reality of AWS migrations in 2026 and beyond. The industry does not pay top dollar for engineers who only know how to click migrate in the AWS console. They pay for leaders who can look a panicking CFO in the eye during a 2 a.m. DNS failure, calculate the blast radius of a ransomware attack, and decisively architect a solution under extreme pressure. You now possess 92 reference-grade, field-tested scenarios. Take these trade-offs, internalize the failure modes, and use them to command the room in your next interview, client pitch, or production cutover. Thank you for watching the Ultimate AWS Cloud Migration Specialist Masterclass. Build securely, execute ruthlessly, and I will see you in the next one.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The Elite Transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the Masterclass.
For more exciting tips, tricks, and more importantly, for valuable insights of interviews, please share, like, and subscribe to my channel. It has a lot of valuable information about various insights of interviews. It has a wide range of real-world portfolio projects of various technologies for interviews, and it has wide range of most asked interview questions and answers of various technologies like data science, SAP, AWS, DevOps, and full-stack web development, and more. That will be useful during interviews. It has a wide range of most asked interview questions and answers and real-world portfolio projects of various technologies for freshers, for 2 to 3 years, experienced candidates, and for 5 or above years, experienced candidates to test their skills by knowing most asked interview questions and make themselves ready for interviews.